252 million years ago, on a coast that no longer exists, a wave broke against warm sand. Nothing seemed wrong. The water was still blue. The sky was still open. A small therapsid, one of your distant ancestors, walked along the tide line, nosing through the seaweed for stranded fish. It was a Tuesday, geologically speaking, or a Thursday. It makes no difference. No one was counting. And above that coast, without anyone noticing, the sky had begun to thin. 30 kilometers up in the stratosphere, ozone molecules were being stripped away by chlorine and bromine compounds that had no business being there. The ultraviolet light slipping through was not yet lethal. It was only the first whisper of it. But that whisper was enough to start rewriting pollen grains in the forests below, giving them deformities that geologists, hundreds of millions of years later, would recognize as the fingerprint of a sky coming undone. This is how the worst catastrophe in the history of life began. Not with a bang, with a thinning. In the 60,000 years that followed, a span of time so short that most of Earth's history couldn't even feel it, 96% of all species on the planet died. Not in one event, in a cascade. The oceans warmed, and then they suffocated, and then they turned sulphurous, and then they burned. The forests of the tropics, some of the richest the planet has ever grown, collapsed in a geological heartbeat and stayed collapsed for 5 million years. The air itself became a weapon, and when it was over, the world was quieter than it had been for 200 million years. Paleontologists call this the end Permian mass extinction. Most people who know it at all know it by a blunter name, the Great Dying. It is the largest wound life has ever suffered on this planet, and nothing since has come close. The asteroid that ended the age of dinosaurs killed about 75% of species. The Great Dying killed 96%. It is not the cousin of the dinosaur extinction. It is an event of a different order entirely, and for a long time afterwards, the Earth was something like an empty stage, waiting for a new cast to walk on. And here is what makes this story strange. The planet survived. It took time, millions of years. The healing was uneven, incomplete, sometimes reversed. But life returned. Smaller at first, then larger. Simpler, then more complex. The survivors of the Great Dying were not glamorous creatures. They were tough, opportunistic, often unremarkable. One of them, a pig-sized burrowing herbivore called Lystrosaurus, inherited almost the entire planet for a while. And from the descendants of those survivors, through a long and unlikely chain, came the reptiles that became dinosaurs, the small furred things that became mammals, and eventually the animal that is listening to this voice right now. So the Great Dying is not only a catastrophe story, it is also, in a certain sense, a creation story. Without it, the world we know would not exist. But to understand why it happened, we have to resist the temptation to start with the drama. Most documentaries about this event open with erupting volcanoes and dying oceans, and then try to explain afterwards why those things mattered. We are going to do the opposite. Because the power of this story doesn't come from the spectacle. It comes from the inevitability. Once you understand the mechanism, once you see how carbon becomes heat, how heat becomes suffocation, how suffocation becomes poison, you stop asking how the Great Dying happened and start asking how it could possibly have gone any other way. The mechanism is what we'll build first. Everything else follows from it. At the center of the story is a region of Siberia that today looks, from a helicopter, like stacked black staircases rising out of the tundra. These are the Siberian traps, and they are the remains of one of the largest volcanic events in the last 500 million years. Over roughly 2 million years, they buried an area about half the size of Europe under basaltic lava, but the lava itself was not the problem. The problem was what the lava traveled through. Beneath Siberia, buried under the surface, lay thick layers of coal and salt, hundreds of millions of years of accumulated carbon, stacked like a pantry waiting to be set on fire. And when the magma began to force its way sideways through those layers, instead of erupting cleanly to the surface, it did something much more dangerous. It cooked them. The coal released carbon dioxide, the salts released halocarbons that climbed into the stratosphere and tore holes in the ozone layer. The carbonates released more carbon dioxide still, and all of it went into an atmosphere that had no way to absorb it fast enough. Over about 75,000 years, carbon dioxide levels in the air rose from around 400 parts per million to more than 2,500, 6 times higher. The world warmed by 8 degrees. And then the cascade began. Warm oceans hold less dissolved oxygen. As the water heated, the oxygen thinned. Deep sea circulation slowed. Layers of ocean that had been mixing for millions of years began to stratify and stagnate. In the dark, anoxic water near the seabed, ancient bacteria that had been dormant since the beginning of complex life woke up and began to breathe sulfur instead of oxygen. The gas they produced, hydrogen sulfide, built up in the deep ocean until it could build up no further. And then it came to the surface. On land, something even more uncanny was happening. A team of researchers led by Yadong Sun published a paper in 2024 that offered an answer to a mystery paleontologists had argued about for decades. Why did life on land die first? The marine extinction was staggering, but it happened tens of thousands of years after the terrestrial one. What killed the forests before the sea even noticed? The answer, Sun and his colleagues argued, was a Mega El Niño. Today, an El Niño lasts 9 to 18 months. It rearranges weather across half the globe, turning wet places dry and dry places wet for a year or so, and then it passes. During the Great Dying, El Niño conditions locked in for decades at a time. Droughts that ran for 10 years were followed by floods that ran for years. Forests couldn't survive the swings. They died, and once they died, they stopped pulling carbon out of the air. And when the carbon sponge of the tropics collapsed, nothing in the Earth system could slow the warming down. Nothing did slow it down, not for 5 million years. So this is the story. Siberian lava cooking carbon out of buried rock. An atmosphere that warmed faster than the oceans could mix. Forests dying in a climate that had learned to swing. An ocean that lost its oxygen, then its pH, then its chemistry. A sky that lost its shield. And at the end of it, in the tropics, sea surface temperatures close to 40 degrees and land temperatures above 50. Temperatures at which photosynthesis stops, at which animals with high metabolism simply cannot function, at which the equator of the planet becomes uninhabitable and stays that way for longer than any mass extinction before or since. 96%. That is the number most people remember, and it is the right one to remember. But the number is not the story. The story is how one thing became another, and how that second thing became a third, and how each step in the chain made the next step not just possible, but inevitable. And underneath all of it, there is a stranger thought. This planet has now hosted complex life for about 500 million years. In that time, it has been through 5 of these events, 5 moments when most of what was alive stopped being alive. And after each of them, it rebuilt. Not the same life, but life. Different, smaller, stranger, eventually richer. The Permian forests never came back. Neither did the trilobites that had ruled the seas for almost 300 million years before that. But something came. It always has. This is the philosophical ground beneath everything we're going to talk about. The Earth is not fragile. It is something much more unsettling than fragile. It is patient. It has seen worse than anything we are likely to throw at it. What is fragile is the particular configuration of life that happens to exist at any given moment. The corals and mammals and temperate forests and coastal cities that make up the world a human being is born into. That is what the Great Dying destroyed. That is what the asteroid destroyed. That is what, in a long enough view, gets destroyed every time. And every time, the planet shrugs and starts again. Before we walk into this story, and it is going to be a long walk down through volcanism and chemistry and suffocation and eventually back up into recovery, there's something small. If this kind of thing is what you came here for, if the long geological view is the kind of company you want in the quiet hours, consider subscribing to The Long Winter. The channel exists for nights like this one. And before you settle in, leave a comment and tell us where you're listening from. What city, what time zone, what hour it is for you. It's a small ritual and it makes the quiet feel less quiet. Now, to understand what was lost, we have to see what was there. The Permian world at its end was not a dying world, not yet. It was one of the most productive biospheres the planet has ever grown. Vast forests in what would one day become southern China, dripped with the leaves of tree-sized plants that no longer exist anywhere on Earth. Shallow seas along the edge of a supercontinent teemed with reef builders and armored fish. And walking through the interior, under a sky that was already a few degrees warmer than our own, the ancestors of mammals and the ancestors of reptiles had begun, tentatively, to share a world. Let's go there. The world 252 million years ago had only one continent. There were not several landmasses drifting apart with oceans between them, the way the map looks today. There was just one vast, irregular shape stretching from pole to pole, surrounded on all sides by a single enormous ocean. The continent was called Pangaea, which simply means all land, and the ocean around it was called Panthalassa, which means all sea. The names are blunt because the geography was blunt. There was no Atlantic, no Pacific, no Indian Ocean. There was only the world ocean and the world continent, and a long, warm gulf that pressed into the eastern edge of the landmass, like a bite taken out of an apple. That gulf was the Tethys Sea, and its shallow, sunlit waters held some of the most spectacular reefs the planet has ever built. Imagine standing on a beach on that Tethys coastline, somewhere near what will one day become southern China. The light is tropical, but softer than you might expect, filtered through an atmosphere slightly hazier than ours. The sand underfoot is pale and fine, made of broken shells and coral fragments, and the skeletons of billions of tiny organisms that have settled here over millions of years. Behind you, the land rises into a forest unlike anything alive today. In front of you, the water is clear enough to see 30 meters down, and what you can see through it does not behave like a modern reef. The corals are the first thing that looks wrong. They are not the branching, cauliflower-shaped corals that build the Great Barrier Reef. These are squat, heavy structures, some of them shaped like stacked cups, others like horns curving up from the seabed. They belong to two groups, the rugose corals and the tabulate corals, that dominated the oceans for 300 million years and will not survive what is coming. At the base of those corals, between them and crawling across them, are brachiopods. To a modern eye, they look like clams, but they are not clams. They are a different branch of the tree of life, one that ruled the shallow seas of the Paleozoic for so long that scientists still use them as the defining fossils of that entire era. In the late Permian, brachiopods come in more varieties than clams do today. They are the small, patient monarchy of the seafloor. Among them drift the last of the trilobites. This matters because almost every schoolchild who has ever held a trilobite fossil assumes they were dinosaur-era creatures. They weren't. By the late Permian, trilobites had already been around for more than 250 million years. They had survived 3 earlier mass extinctions, adapted through glaciations, crawled across the floors of vanished oceans. A few species were still here, clinging on, and in another 100,000 years, they would be gone forever. You are looking at one of the longest-running experiments in animal form that life has ever attempted in its final generation. Turn and walk inland. The forest begins almost at the high tide mark and rises behind it in layers, the way a tropical rainforest does today, but the species composition is entirely strange. The tallest trees are lycopods, relatives, very distantly, of modern club mosses, but here they have grown to 30 meters or more, with trunks covered in diamond-patterned scars where their leaves have shed. Below them, a middle canopy of seed ferns and tree ferns holds the humid air close to the ground. And threaded through that canopy, climbing and spreading, are the gigantopterids, a group of plants that nobody alive today has seen because nothing quite like them exists anymore. Their leaves are enormous, sometimes bigger than a human torso, with intricate networks of veins that modern botanists recognize as a rainforest signature. Those drip tips, those vein networks, those giant leaves, they are the unmistakable signs of a wet, warm, nutrient-hungry forest, pulling water and carbon through itself at a rate that makes it one of the most productive biomes the planet has ever supported. There is also something missing from this forest, and noticing the absence takes a moment. There are no flowers. Flowering plants will not evolve for another 100 million years. There are no grasses. Grasses will come later still. There are almost no sounds above the level of the insects, because there are no birds. Birds are still a long way away in the future, waiting inside a lineage that hasn't even started yet. What you hear standing in that forest is the creak of wind through scaly trunks, the occasional rustle of something moving in the understory, and the constant, layered hum of the richest insect fauna the Earth has ever produced. Dragonflies with wingspans 1/2 meter across, cockroaches the size of a hand, beetles everywhere. If you wait quietly, you will see the something in the understory, a dicynodont, maybe the size of a pig, stubby-legged and heavy-bodied, with a beaked face and 2 downward curving tusks. It is browsing on the low ferns, unhurried. It has no reason to be hurried. Predators exist in this world, but they are not what you would expect either. There are no wolves, no big cats, no crocodiles, none of those lineages are born yet. Instead, the apex predators of the late Permian are the gorgonopsids, and a gorgonopsid would be, to a modern observer, a genuinely disturbing animal to look at. They are mammal-line reptiles, closer in ancestry to you than to any lizard, and they carry themselves with the low, slung-shouldered gait of a big hunting animal. Their skulls are long and narrow, armed with saber-like canines that some species could grow to 12 centimeters. They probably had some primitive form of whiskers. They may have been partly warm-blooded. They are, in almost every way that matters, the first animal on Earth that looks a little like a predator in the modern sense, and they will be gone before the Triassic begins. These creatures, the dicynodonts, the gorgonopsids, the small agile cynodonts that will eventually give rise to mammals, all belong to a group called the therapsids. That word is worth holding on to because the therapsids are the reason this world matters to us personally. The animal listening to this right now descends through an unbroken chain of survivors and reinventions and evolutionary chance from a small therapsid that lived somewhere on Pangaea in the final million years of the Permian. Your ancestors were in this forest, not abstractly, literally. Now pull back, far enough to see the whole continent. The reason Pangaea's climate worked the way it did comes down to geometry. When you take all the world's landmass and fuse it into one piece, You create problems that do not exist on a planet with scattered continents. Heat cannot circulate properly. Moisture cannot penetrate far inland. Ocean currents have to run around the edges of the supercontinent instead of threading through it. The result during the Permian was a climate system driven by what geologists now call a mega monsoon, a global seasonal reversal of winds on a scale that dwarfs anything the modern world produces. In the wet season, vast amounts of moisture were dumped on the coastal belts of the supercontinent, feeding those Tethys rainforests. In the dry season, the interior of Pangaea baked. Deserts stretched across the heart of the landmass that would have been genuinely hostile to any large animal. The red beds of modern Texas and Oklahoma, those dry, rust-colored sedimentary layers that fossil hunters love, are what those Permian interiors left behind. So Pangaea was a continent of extremes, lush along the edges, brutal at the center. Its climate was already swinging harder than any modern continent's. Its interior already hot, its coasts already wet, its atmosphere already carrying slightly more carbon dioxide than ours. The whole system was, in a phrase that researchers now use, a super Australia, a landmass big enough and arid enough that its weather worked differently from any place on Earth today. This is worth dwelling on because it explains something about the catastrophe to come. Pangaea was not a stable world tipped over by sudden violence. It was a world already sitting on a knife's edge, holding itself together through a climate system that worked, but barely. A small push in the wrong direction would knock it over. A large push would not just knock it over, it would send it tumbling down a slope built out of feedback loops, each one amplifying the last. And in about 100,000 years, the push was coming. For now, though, the forest is quiet. The dicynodont finishes its ferns and moves on. A dragonfly lifts off a branch, lands somewhere else. Out on the reef, a brachiopod closes its shell against a drifting current. The sun is still high, the air is still sweet. None of the living things in this world have any way of knowing that 2,000 kilometers to the north, buried kilometers beneath a cold plateau that will one day be called Siberia, something has just begun to stir. A movement so slow and so deep that it will take tens of thousands of years to rise. The therapsids cannot sense it, the corals cannot sense it, the gigantopterous forest, drinking the morning air, cannot sense it, but it has started, and once it starts, nothing in this world has the capacity to stop it. The Permian world was not dying. It was living harder than almost any world has lived, in the last full inhale before a breath that would never quite be completed. Long before anything happened on the surface, the damage was already being done in the dark. This is worth understanding before we go anywhere else, because the usual image of a volcanic catastrophe, red fountains of lava, pyroclastic clouds rolling down a mountainside, cities vanishing under ash, is almost exactly wrong for what happened in Siberia. The Great Dying was not a surface event that leaked downward into the oceans and the atmosphere. It was a deep event that took tens of thousands of years to reach the surface at all, and by the time it did, most of its work was already complete. The lava, in the end, was almost a side effect. The real killer was something quieter, and it was happening underground. To understand why, we need to look at what was underneath Siberia in the late Permian. The continent that would become Russia was, at the time, a relatively stable piece of crust sitting in the northern latitudes of Pangaea. Beneath its surface, however, lay a geological archive of extraordinary density. Hundreds of millions of years of sedimentary rock had accumulated there, layer after layer of limestones and dolomites, thick beds of salt and gypsum left behind by ancient evaporating seas, and above those, enormous deposits of coal laid down during the Carboniferous, when swampy forests had dominated the planet and left their carbon behind. If you had drilled down through that crust in the Permian, you would have passed through what amounted to a stacked pantry of stored carbon and volatile compounds. Coal near the top, limestone deeper, salts and halides below that. Everything necessary, in other words, to build a climate weapon, already assembled and waiting for a trigger. The trigger, when it came from below. Somewhere in the Earth's mantle, a plume of superheated rock began to rise. Mantle plumes are slow-moving, enormous phenomena, and geologists still debate the details of how they form. But their effect on the surface is consistent. They deliver vast quantities of heat and magma to the base of the continental crust, and when they arrive, they remake whatever landscape sits above them. The Siberian plume arrived late in the Permian, and it was one of the largest such events the planet has ever produced. Over the next 2 million years, it would generate enough magma to bury an area roughly the size of modern Europe under flood basalt, a volcanic province so vast that geologists named it simply the Siberian Traps, from an old Germanic word for stairs, because weathering later carved the hardened lava into landscapes that looked like giant staircases climbing the tundra. But here is where the story diverges from what you might expect. For the first several 100,000 years of this event, magma did exactly what magma usually does in a place like this. It rose through fractures in the crust, broke the surface, and erupted in great sheets of basaltic lava that spread across the Siberian landscape. These eruptions were enormous. They poured out more lava in a single century than the entire output of modern volcanism in 1,000 years. And yet, during all that time, the global biosphere showed almost no sign of distress. Carbon cycles remained stable. Species diversity held steady. The fossil record, read across those first 300,000 years of Siberian volcanism, looks essentially normal. Something changed very rapidly near the end of that period, and what changed was not the scale of the volcanism, but its style. Up to that point, the magma had been erupting. After that point, it began increasingly not to erupt at all. Instead, it spread sideways, forcing its way horizontally between existing layers of sedimentary rock, cooling in place as vast sheets called sills. A sill, in simple terms, is a slab of igneous rock that intruded into sedimentary layers instead of breaking through to the surface. Picture a hot knife sliding between the pages of a book. The knife never reaches the cover, it just spreads laterally, heating everything it touches from within. This is the moment that researchers now point to as the true trigger of the Great Dying. A team led by Seth Burgess, using high-precision dating of zircon crystals from Siberian rocks, established the timing beyond reasonable doubt. The onset of sill emplacement lines up with the beginning of the mass extinction with a precision of tens of thousands of years. When the Siberian magma stopped erupting and started intruding, the biosphere began to fail. The reason why takes us back to the stacked pantry beneath the Permian surface. When a sill forces its way into a layer of coal, the coal does not burn in the open-air sense. It is cooked under pressure in the absence of oxygen at temperatures of hundreds of degrees. The process releases carbon dioxide in quantities that a surface-burning fire could never approach, and it also releases something more dangerous: methane, a greenhouse gas more than 80 times more potent than carbon dioxide on short timescales. When a sill intrudes into a layer of carbonate rock, the same thermal process drives out yet more carbon dioxide, baked out of limestone the way quicklime is produced today. And when a sill intrudes into a layer of evaporate salt, something genuinely strange happens. The salts, heated to magmatic temperatures, release halogen compounds, chlorine and bromine bound to organic carbon, forming methyl chloride and methyl bromide. These are not climate gases. These are ozone-destroying gases. They are the same family of compounds that humans, in the 20th century, almost accidentally used to tear a hole in the modern ozone layer before the practice was banned. So a single sill, forcing its way through the wrong layer of rock, could release 3 distinct classes of atmospheric poison at once. Greenhouse gases to warm the planet, halocarbons to strip its ultraviolet shield, and vast quantities of sulfur dioxide pulled out of sulfide-rich sediments to acidify the rain. This is the mechanism, and once you see it clearly, the sequence of what happens on the surface becomes almost inevitable. The Earth above Siberia did not need to be continuously erupting to be in trouble. It needed only to keep cooking. As long as fresh magma was intruding into fresh sediment, the gases would keep rising. And over the next several tens of thousands of years, that is exactly what happened. Pulse after pulse of sill emplacement, each one dumping more carbon and more halogens and more sulfur into the atmosphere until the chemistry of the air itself began to shift. There is one more detail worth holding on to because it explains why this particular volcanic event, out of all the large volcanic events in Earth's history, produced the worst catastrophe. Large igneous provinces are not rare. The planet has built several of them. The Deccan Traps of India, which erupted around the time the dinosaurs died, were comparable in raw volume to the Siberian traps. The Central Atlantic Magmatic Province, which triggered the end Triassic extinction, was comparable as well. But neither of those events killed anywhere close to 96% of species. What made Siberia special was the pantry. The Deccan Traps erupted through mostly oceanic crust and continental rock, without particularly rich carbon reserves beneath. The Siberian Traps erupted through some of the thickest accumulations of coal, salt, and carbonate ever assembled in one place. It was, in a brutal geological sense, a case of bad luck. The right volcano arriving at the right spot to detonate the right archive. Or, from another angle, it was the planet setting itself up to demonstrate how much damage a coincidence could do. For now, standing on the surface of Pangaea, you could walk across Siberia and see almost no sign of what was happening beneath your feet. A few fissure vents, perhaps, somewhere on the horizon. Occasional lava flows in the distance. No sense of urgency. The animals still hunted, the rivers still ran. The forests along the Tethys coast still breathed. But under that surface, kilometers down, the sills were advancing. The coal was heating, the salts were decomposing, and every year, invisible and odorless, a little more carbon dioxide and a little more methyl chloride and a little more sulfur were leaking into the air. Nothing in the Permian biosphere was built to detect a slow poisoning of the atmosphere. That is why the Great Dying could approach for tens of thousands of years without warning. By the time anything measurable began to change, by the time the first reefs started to struggle, the first forests to brown, the chemistry had already shifted past the point where the system could recover on its own. The dose had been delivered. What remained was the waiting. And the waiting did not last long. The first sign that anything was wrong, as far as the planet was concerned, was a line on a graph that nobody was there to draw. Over the course of roughly 75,000 years, the carbon dioxide concentration of the Earth's atmosphere climbed from a level not far from what we have today, around 400 parts per million, to something close to 2,500, 6 times higher, a planet-wide chemical shift that would, in purely atmospheric terms, remake the entire climate system. This happened gradually, and that gradualness matters. 75,000 years is a long stretch in human terms. It is roughly 7 times the entire duration of recorded civilization. Spread out over that span, the year-to-year change in carbon dioxide would have been too small for any living creature to notice, and too small even to register in most forms of sedimentary rock. What accumulated was not a shock, but a drift, a steady, quiet increase that the biosphere had no mechanism to object to, because nothing in the biosphere was designed to track the slow poisoning of its own air. The effect of that drift, though, was not gradual at all. It was cumulative, and cumulative things have a way of looking gradual until they don't. The physics of what carbon dioxide does in an atmosphere is old science, and it is worth walking through carefully, because this is the point in the story where everything else begins. A molecule of carbon dioxide is transparent to visible light, the way the air around you is transparent. When sunlight arrives at the Earth, it passes through the carbon dioxide and strikes the surface, and the surface absorbs it and warms up. Then, because everything that is warm radiates heat, the surface sends that energy back out, not as visible light, but as infrared. And this is where carbon dioxide stops being transparent. Infrared passes through it poorly. The molecule absorbs it, vibrates, re-emits it in all directions, and a significant fraction of that re-emitted energy travels back down to the surface instead of escaping to space. The surface warms further. The warmer surface radiates more infrared. More of that infrared is intercepted, and the system finds a new equilibrium at a higher temperature. Double the carbon dioxide, and you raise the global average temperature by something on the order of 3 degrees. Multiply it by 6, as the late Permian atmosphere did, and you get a thermal shift of a magnitude that the planet has rarely attempted. Oxygen isotopes preserved in the fossilized teeth of tiny eel-like creatures called conodonts, collected from Chinese rock sections with extraordinary patience, tell us what happened. Surface ocean temperatures in the low latitudes rose by roughly 8 degrees. The tropical oceans, which had spent the Permian hovering between 25 and 28 degrees Celsius, began climbing past 32, past 33, heading for a threshold that no one, before this research, had even considered physically possible. But the temperature rise was only the first thing. The temperature rise triggered a cascade of changes in the oceans that would turn out to matter more than the heat itself. The first of those changes was a simple piece of chemistry. Oxygen dissolves in water. This is what allows fish to breathe. And the amount that can dissolve depends on the temperature of the water. Cold water holds a great deal of oxygen. Warm water holds less. If you heat the ocean by even a couple of degrees, the total amount of dissolved oxygen available to marine life drops because the physical capacity of the water to carry oxygen has been reduced. Heat the ocean by 8 degrees and the reduction is severe. The oceans of the late Permian were not yet poisoned, they were not yet stratified, but they were breathing harder and every organism in them was feeling the difference. The second change was geometric. The Earth moves heat from equator to poles primarily through ocean circulation, through the great overturning currents that sink cold water near the poles and draw warm water up from the tropics. That circulation works because cold polar water is denser than warm tropical water, and density differences are what drive the motion. When the whole ocean warms, those density differences shrink. The circulation slows. Heat stops moving efficiently. The equator warms further because its heat is not being carried away, and the polar waters warm too, because there is no longer enough cold, deep water being formed to balance the system. This is a feedback, and feedbacks are where climate systems become dangerous. A small warming leads to a sluggish circulation. A sluggish circulation leads to a warmer equator. A warmer equator leads to more warming. None of these steps is dramatic on its own, but chained together, they produce temperatures at the tropics that the planet was not built to sustain. There is a third thing that was happening, quieter than the other two, and this one is a detail that only became clear to researchers in the last few years. When the oceans warm and the circulation weakens, the patterns of atmospheric pressure above the oceans begin to behave strangely. Winds that had been steady become variable. Rainfall patterns that had held in place for millions of years start to wander. And the climate system begins to exhibit a kind of instability that modern climatologists recognize because we have a name for it. We live with a small version of it every few years. But that particular thread is worth following in its own right. and we'll pick it up soon. What matters for now is what a Tethys shoreline would have felt like to something living on it, at the point when the drift had become measurable, but before the real catastrophe began. Imagine yourself there, on a warm afternoon near the end of the Permian, standing at the edge of a shallow reef. The water is still blue, the corals are still standing. But you would notice things. The water on your ankles is warmer than it should be for the season, not dangerously warm, but warmer. Further out, the reef looks faintly wrong. Some of the coral colonies are pale at their tips, bleached the way modern corals bleach when stressed, though you don't know the word. Brachiopods are smaller than they used to be. The fish move less. The reef is not dying. It is tired, and it does not yet know what tiredness means on the geological scale it has entered. Pull yourself above the surface of that water and look at the sky. The sun is bright and a little hazy. The air smells right. The clouds look normal. But if you could sample the air with any modern instrument, you would find the carbon dioxide approaching 1,000 parts per million, and then 1,200, and then 1,500. The numbers climbing year by amounts too small to see, but too large to stop. The thermal momentum of the system is already locked in. Even if the Siberian sills stopped intruding tomorrow, and they will not stop for hundreds of thousands of years, the oceans would continue warming for decades, absorbing the heat that the atmosphere has already stored. None of the animals in this world can register what is happening. They have no cultural memory, no instruments, no vocabulary. A brachiopod does not know it is being asphyxiated by a degree at a time. A gorgonopsid does not know that the forests are beginning to thin, or that the water in its drinking pool tastes faintly of something that wasn't there 1,000 years ago. The catastrophe is not being witnessed. It is only being survived less well every year by creatures that have no means of understanding their own distress. And yet the system was already moving towards something new. Not a simple warming, not just a stressed ocean. Something that, when the modelling work of a team in Wuhan and Bristol finally cracked it open in 2024, would rewrite how scientists think about the entire extinction. Because the question that had bothered paleontologists for decades, the question of why the land died first, tens of thousands of years before the oceans, had an answer hiding inside that thermal instability. It was not obvious. It took decades of collecting conodont teeth and running climate simulations to pull it out of the rock. But it was there. The warming was doing something to the weather, and what it was doing had a name that every modern listener already knows. The name is El Niño, and almost everyone listening to this has lived through one. They arrive every few years, unannounced and short-lived, and they rearrange the weather of half the planet for somewhere between 9 and 18 months. A strong El Niño can push drought across the Amazon, flood the deserts of Peru, warm the Pacific to the point that coral reefs bleach and fisheries collapse. The El Niño of 2023 and 2024 was one of the strongest on record, and its fingerprints showed up in wildfires from Canada to Australia, in heat waves that broke temperature records on every continent, in the warmest global year since measurements began. It was, for a modern planet, a severe event. It lasted about a year. In the late Permian, an El Niño-like state locked in and did not leave for decades. This is the finding that a team led by Yadong Sun at the China University of Geosciences, working with modelers at the University of Bristol, published in Science in September of 2024. And it resolved a problem that had puzzled paleontologists for a long time, because the fossil record across the Permian-Triassic boundary has always shown something strange, something that the standard story of the Great Dying could never quite account for. Life on land died first. The forests began to fail, the insects began to disappear, the terrestrial vertebrates began to collapse, tens of thousands of years before the marine extinction began, and that order made no sense. If the killer was carbon dioxide released by Siberian volcanism, if the mechanism was global warming, then the oceans and the land should have suffered roughly together, because warming is a global phenomenon and it does not respect coastlines. Instead, the land went first. And for decades, nobody could say why. Sun and his colleagues approached the problem the way a detective might approach a cold case. They gathered oxygen isotopes from 15,000 fossilized conodont teeth, the tiny, durable mouthparts of extinct eel-like creatures that lived in shallow seas all over the late Permian world. The ratio of oxygen isotopes in a conodont tooth records the temperature of the water the animal lived in, because the chemistry of that ratio depends on how warm the water was when the tooth was forming. By mapping temperatures across thousands of conodonts from different parts of the ancient ocean, the team produced something no one had produced before, a thermal portrait of the late Permian world, latitude by latitude from east to west, across what used to be the world ocean. What they found was a pattern. Before the extinction, the oceans on either side of Pangaea behaved the way the Pacific behaves today, warmer on the western side, cooler on the eastern side, with steady trade winds piling the heat up where it belonged. As the extinction approached, that pattern began to break down. The thermal gradient flattened. Warm water started to drift east, the way it does during a modern El Niño, when the Pacific's normal structure temporarily inverts. Except the Permian version didn't temporarily invert. It stayed inverted, and then it inverted harder. The reason, when the modelling team worked it out, came down to the geometry of Pangaea itself. A single supercontinent stretching pole to pole produced a climate system uniquely vulnerable to this kind of runaway. The thermal contrast between land and ocean was enormous. The ocean currents had nowhere to circulate freely, and as the atmosphere warmed from Siberian carbon dioxide, the delicate machinery that kept the trade winds blowing in their normal direction began to weaken. Weaker trade winds meant less heat pushed to the west. Less thermal contrast meant weaker trade winds still. The feedback tightened around itself, and the climate shifted into a state that researchers now describe with a phrase that does not really exist in modern science: a Mega El Niño. What that meant on the ground was a rhythm of disasters that no ecosystem evolved on Earth could tolerate. Imagine living somewhere along the southern coast of what is now China in a gigantopterous forest, not unlike the one we walked through at the start. For most of your species' history, the rains have arrived reliably every year. The rivers have run, the soil has held. Now the rains stop, not for 1 year, not for 3, for 10 consecutive years, maybe more. Almost no rain falls. The canopy begins to thin. The ferns of the understory brown and die. The rivers reduce to a trickle, then to a line of stagnant pools, then to dry channels. The decinodonts, your abundant herbivores, begin dying by the thousands where the water used to be. The gorgonopsids, their predators, follow. Fires that would have been impossible in the wet old forest begin running through the dry, dead canopy, releasing yet more carbon into an atmosphere that cannot absorb it. And then, just when the land has adapted, barely, to drought, the rains come back. Not normally. Floods, years of floods, water that the exhausted soil cannot absorb, running off into torrents that carry topsoil away by the million tons. Rivers that had forgotten their channels overflow into new ones. The plants that managed to cling on through the drought are drowned. What had been a desertifying forest becomes a swamp, then a washed-out plain. And after a few years of this, the droughts return. This is what Paul Wignall, one of Sun's collaborators, described as a climate that was, in his words, all over the place, swinging from extreme to extreme on timescales that no multicellular organism had ever been asked to endure. Plants could not set seed in the wet years because their root systems had been broken by the dry. Insects could not complete their life cycles. The large herbivores starved in the droughts and drowned in the floods. And every generation of death pulled more carbon out of the soil, dumped more of it into the atmosphere through decomposition and fire, and fed the warming that was driving the climate swings in the first place. This was why the land died first. The oceans, for a while, were buffered. Water has an enormous thermal mass, and even as the surface waters warmed, the deeper oceans stayed cool enough to keep the shallow marine ecosystems functioning. Stressed, yes. Thinning at the edges, yes, but still alive. The terrestrial world had no such buffer. When the climate started swinging, the forests had nowhere to retreat to. The insects, usually among the most adaptable creatures on the planet, showed the collapse clearly in the fossil record. One by one, lineages that had thrived for hundreds of millions of years simply stopped appearing. Beetles, cockroaches, some of the dragonfly families survived by accident of life cycle, hanging on through the aquatic larval stages that could exploit the brief wet intervals. Everything else went. Sun put it bluntly when he discussed the findings. The temperature swings on land pushed beyond the thermal tolerance of most species at a rate so rapid that evolution could not adapt. Only those things able to migrate quickly survived, and there were not many plants or animals that could do that. A forest cannot pick up and move. A dicynodont, if the drought lasted long enough, could not walk out of it. There is something else in this story worth holding on to, because it is one of the cleanest examples in deep history of what feedback loops do when they find the right geometry. The Siberian traps alone should not have produced a mass extinction of this scale. The atmospheric carbon load by itself was serious, but not annihilating. What turned the event from a crisis into a catastrophe was Pangaea. The shape of the supercontinent primed the climate to collapse in this particular way, to respond to a carbon pulse by generating an El Niño that would not end. It was, in a certain sense, a geographic accident, a consequence of where the continents happened to be at the moment the traps erupted. A different world with the same volcanism might have suffered a hot and unpleasant few 100,000 years and recovered. The Permian world, with its particular arrangement of land and ocean, spiraled into a runaway. And the runaway, once it started, had a further problem. Because when the forests of the tropics died, when 10 years of drought followed by years of flood had finally finished them off, they took something with them that the atmosphere had depended on for hundreds of millions of years. Plants, in their vast collective biomass, are the planet's carbon sponge. They pull carbon dioxide out of the air and lock it, through photosynthesis, into living wood and leaf and soil. A healthy tropical forest can absorb enormous quantities of the gas. A dead one cannot. And as the Gigantopterous forests collapsed, the mechanism the Earth had relied on to damp down its own warming began, for the first time in the story, to fail. The carbon kept coming out of Siberia, and now there was nothing left to take it back in. A forest is not, at first glance, a piece of climate machinery. It is a landscape. It is trees and understory and birds, or in the Permian, insects, and the green, self-organizing complexity that a human walking through it experiences as beauty. But in terms of what it does for the planet, a forest is something more specific. It is a sink. It is the part of the carbon cycle that pulls carbon dioxide out of the atmosphere and locks it, through photosynthesis, into living tissue and soil. A single mature tropical tree can sequester many tons of carbon over its lifetime. Multiply that by the billions of trees in an intact rainforest, add the carbon stored in the soil beneath them, and you get a regulator, a massive, continuously operating regulator that keeps atmospheric carbon from running away. When the Siberian traps began venting carbon into the Permian atmosphere, this regulator was the Earth's primary defense. Every ton of carbon dioxide the volcanoes released, the forests pulled some fraction of it back. Not instantly, not completely, but enough to matter. Enough to slow what was happening. Enough, under normal conditions, to keep the system from tipping. The forests of the late Permian tropics were among the largest carbon sinks the planet has ever grown. The gigantopteris rainforests of what is now southern China, the seed fern forests of Gondwana, the coal-forming swamps of Cathasia. Together, they represented a vast green machinery, absorbing enormous quantities of carbon year after year, century after century, without complaint. And for most of the extinction events so far, they had done exactly that. Even as the climate warmed, even as the Mega El Niño began its decades-long swings, the forests had kept working, stressed but alive, taking carbon out of the sky faster than any other system on the planet. When they finally went, they went all at once. The cascade that killed them is worth walking through carefully because it demonstrates something that modern climate science still struggles to communicate to a general audience: that ecosystems do not usually degrade in proportion to the stress placed on them. They absorb, they absorb, they absorb, and then at some threshold, they collapse. The collapse is not gradual. The collapse is the point at which accumulated damage overwhelms the capacity of the system to repair itself, and once it starts, it does not slow down. For the gigantopteris forests, that threshold came in the form of water. A rainforest is not, despite the name, simply a forest that receives a lot of rain. It is a forest that has co-evolved with a particular pattern of rainfall, and that pattern is narrow. Too little water for too long, and the canopy begins to die. Too much water, delivered too fast, and the root systems drown. A healthy tropical forest can survive a dry year. It can survive a wet year. What it cannot survive is a climate that alternates unpredictably between both extremes, because the adaptations required for drought are different from the adaptations required for flood, and no organism can maintain both at once. The Mega El Niño cycles delivered exactly this. A decade of drought would kill off the moisture-loving species, the giant-leaved gigantopterids, the delicate tree ferns, the epiphytes that depended on constant humidity. A few years of flooding would then kill whatever had adapted to the drought. The next drought would take what was left of the wet specialists. The next flood would take what was left of the dry specialists. And with each cycle, the forest became less capable of recovery, because the recovery itself required stability that no longer existed. Add to this the fires. A drying forest builds up fuel. When lightning or volcanic ash ignites that fuel, the fire does not behave like a natural rainforest fire. It behaves like the fires tearing through modern drought-struck regions, consuming vast areas of canopy in single events. The charcoal deposits preserved in Permian-Triassic sedimentary rocks, particularly in what is now Australia and Antarctica, record a spike in wildfire activity that aligns precisely with the onset of the terrestrial collapse. For hundreds of thousands of years before the extinction, fire had been a rare event in these forests. Then, over a geological instant, it became common. And then, after the fires, the erosion. A living forest holds its soil in place through the network of roots that bind the ground together. A dead forest has no such network. When the rains returned after the droughts, they washed the topsoil of entire landscapes into the rivers, and the rivers carried it into the sea. Measurements from sedimentary cores in southwestern China show erosion rates climbing from about 150 tons per square kilometre per year in the late Permian to more than 2,000 tons per square kilometre per year by the early Triassic, more than a 13-fold increase. The continents were bleeding their own soil into the oceans, and the soil was taking with it the last of the nutrients that any recovering forest would have needed to rebuild. The final collapse, when it came, was fast, not fast in human terms. It played out over tens of thousands of years. but fast in geological ones. The Gigantopterous flora, which had dominated the tropics for millions of years, vanished from the fossil record. In its place, a new vegetation appears, small, stress-tolerant plants called lycopsids, particularly a genus called Analepis, which proliferates across the early Triassic landscape the way a weed proliferates through a demolished garden. A lycopsid is not a tree. It is a low, herbaceous plant, the kind of thing that grows knee-high at the edge of a pond. And for several million years after the extinction, nothing in the tropics grew much taller than a lycopsid. Paul Wignall, the Leeds paleontologist who has spent much of his career mapping this event, put it simply. In the early Triassic, he said, nothing would have been growing higher than your knees. A world that had, for 200 million years, been shaded by the canopies of true forests was suddenly flat, open, the horizon visible everywhere. If you had stood in what had once been the Gigantopterous rainforest of southern China, 10,000 years after the collapse, you would have seen scrubland to the edge of your vision, broken only by the occasional surviving fern. The dragonflies were gone, the dicynodonts were gone, the layered, humid, birdless hum of the late Permian was gone. The wind moved through the lycopsids and made the same small sound everywhere. This is the point where the problem stops being about volcanism and starts being about the Earth system itself, because the disappearance of the forests did something to the carbon cycle that the Siberian traps alone could never have done. It removed the regulator. The traps had been pouring carbon into the atmosphere for hundreds of thousands of years, and the forests had been absorbing as much as they could manage. Now the absorption stopped. The atmosphere kept receiving, but it could no longer give anything back. Carbon dioxide that would normally have been drawn down by photosynthesis simply accumulated, and the warming that had driven the forests to collapse in the first place now had nothing to slow it down. A team led by Zhen Xu, working across Chinese and British institutions, spent years reconstructing exactly how much of the post-extinction super greenhouse can be explained by this single mechanism. The results, published in 2025, were stark. The loss of tropical forests, modelled across the Permian-Triassic boundary, accounts for essentially all of the prolonged heat that followed. Without the collapse, the volcanism alone would have produced a bad few 100,000 years and then faded. With it, the climate locked itself into a super greenhouse state that persisted for 5 million years. Xu made a comment about the finding that is worth holding on to. This, she said, is the only high-temperature event in the history of Earth in which the tropical forest biosphere collapses. The two things, the collapse and the duration of the heat, are connected. The planet has survived volcanism before. It has survived warming before. It has not, in the entire 500 million year record of complex life, survived both simultaneously, because the forests are what normally stop the warming from becoming permanent. The echo of that, in a world where the Amazon is currently losing mass year after year, does not need to be pointed out. What matters for the story we are telling is what it meant on the Permian-Triassic boundary itself. The land had now been broken twice. First, by the Mega El Niño climate swings, then by the collapse of the forests those swings had produced. And with the forests gone, with the soil eroding into the oceans, with the atmosphere thickening every year, the system was no longer drifting toward catastrophe. It was committed to it. Whatever happened next would happen to a planet that had already lost its capacity to defend itself. And what happened next, in the oceans, was a chemistry the planet had not experienced in hundreds of millions of years. When carbon dioxide meets water, it does not simply dissolve, it reacts. A molecule of carbon dioxide coming into contact with a water molecule produces carbonic acid, a mild, familiar acid, the same one that gives a freshly opened bottle of sparkling water its bite. Dissolve a small amount of carbon dioxide in a large volume of water, and the effect on the chemistry is barely measurable. Dissolve enormous quantities of it continuously for tens of thousands of years, and the chemistry of the entire ocean begins to shift. This is what happened in the late Permian. The oceans of a healthy pre-industrial Earth sit at a pH of about 8.2, which is to say they are slightly alkaline, closer to the chemistry of baking soda than to anything you would call acidic. That alkalinity is not an accident. It is maintained by a set of buffering reactions between the water, dissolved carbon compounds, and the calcium carbonate skeletons of marine organisms, all of which interact in a chemical dance so stable that the ocean has held roughly the same pH for most of the past 500 million years. Even significant pulses of volcanic carbon tend to be absorbed by this buffering system without much long-term disruption. The ocean drinks the carbon, holds it, and keeps its chemistry steady. But every buffer has a limit. Push enough acid into a buffered system, and eventually the buffer runs out. The pH starts to fall, and when it does not fall gracefully. In 2015, a research team led by Michael Clarkson at the University of Edinburgh published one of the most important pieces of evidence we have for what happened to seawater during the Great Dying. They did it by measuring boron isotopes, specifically the ratio of 2 versions of boron, preserved in fossil brachiopod shells from sedimentary rocks spanning the Permian-Triassic boundary. Boron is exquisitely sensitive to pH. The way it incorporates into a shell depends on how acidic the surrounding water was at the time the shell formed. Read carefully, it functions as a pH record, preserved in stone, readable hundreds of millions of years later. What Clarkson's team found was this: for most of the late Permian, seawater pH held steady, buffered against the slow leak of Siberian carbon. The first pulse of the extinction, when it came, produced almost no change in ocean acidity. The buffer was still working. But then, during the second and more severe pulse of the extinction, when the carbon release from Siberia became massive and rapid, the buffering system failed. The pH of the surface ocean dropped from around 8.0 to about 7.5. Half a unit of pH. Half a unit does not sound like much until you remember how pH works. Every single unit of pH represents a 10-fold change in acidity. A drop of half a unit means the oceans had become roughly 3 times more acidic than they had been within a geologically brief window. For organisms whose survival depended on stable ocean chemistry, this was the chemical equivalent of having the ground move under their feet. The first victims of this shift were the animals that built their bodies out of calcium carbonate. This is a larger group than it sounds. Corals, brachiopods, many mollusks, certain planktonic organisms, the small calcifying algae that form the base of entire marine food webs. All of them construct their shells or skeletons by pulling calcium and carbonate ions out of the surrounding water and assembling them into crystalline mineral. When the water is alkaline, this process is easy. The chemistry favors the assembly. When the water becomes acidic, the chemistry reverses. Carbonate ions become scarcer. The construction of shells requires more energy, and at a certain threshold, the existing shells of living animals begin to dissolve from the outside, faster than the animal can rebuild them. This is what happened across the tropical reefs of the Permian. The great rugose and tabulate corals, which had built the seafloor landscapes of the Paleozoic for 300 million years, could not maintain their skeletons in the new chemistry. Neither could most of the brachiopods. Neither could the calcareous algae that had been producing the fine-grained limestone sediments of the shallow seas. Across something like 60,000 years, these groups disappeared from the fossil record almost completely. The rugose corals would never return. The tabulate corals would never return. When reefs eventually rebuilt themselves tens of millions of years later, they would be built by entirely different organisms. the ancestors of modern stony corals, a lineage that had barely existed in the Permian and that now, in the aftermath of the chemistry collapse, inherited an empty world. But acidification was only part of the kill mechanism. And this is where a newer piece of research, published in 2024 by a team led by Haijun Song at the China University of Geosciences, has changed how scientists think about the selectivity of the Great Dying. Because the extinction did not treat all marine animals equally. Some groups vanished almost entirely, others passed through, diminished but intact. And the pattern of who lived and who died turned out to have less to do with where they lived or what they ate than with something much smaller and much stranger. It had to do with the molecules they used to carry oxygen through their bodies. Animals, at the scale of a brachiopod or a snail, face a fundamental problem. Oxygen needs to get from the water outside their bodies to the cells deep inside them, and diffusion alone only works over very short distances. For anything larger than about a millimeter, evolution has to invent a carrier, a molecule in the bloodstream that can pick oxygen up at one end of the body and release it at the other. Different animal lineages have invented different carriers. Vertebrates use hemoglobin, the iron-based molecule that makes your blood red. Many mollusks use hemocyanin, a copper-based molecule that turns their blood blue. And brachiopods, along with a few other ancient lineages, use hemerythrin, a more primitive oxygen-binding protein that does the job passably in ordinary conditions, but struggles when the surrounding water runs low on oxygen. Haijun Song's team looked at the extinction patterns of marine animals across the Permian-Triassic boundary and mapped them against the oxygen-carrying chemistry of each group. What they found was striking. The lineages that used hemoglobin or hemocyanin, the high-capacity carriers, survived at dramatically higher rates. The lineages that relied on hemerythrin, or on simple diffusion, were hit hardest. Brachiopods, which had dominated the Paleozoic seafloor for 1/3 of a billion years, suffered losses they never recovered from. Mollusks equipped with hemocyanin made it through, and when the oceans finally began to rebuild, it was the mollusks, the clams, the snails, the ancestors of squid and octopus, that took over the ecological roles brachiopods had held for so long. This is why the modern seafloor looks the way it looks. Go to any beach today and you will find clamshells everywhere. You will find brachiopods almost nowhere, though they still exist in small populations in deep, cold water. 252 million years ago, the ratio was reversed. The change is not a coincidence, and it is not the result of competition. It is the result of a moment during the second pulse of the extinction, when the water ran short on oxygen and turned acidic at the same time, and the animals whose biochemistry could handle both stresses walked out of the catastrophe alive, while the animals whose biochemistry could not were erased. What this tells us about the Great Dying is something that paleontologists have been quietly converging on for years. The extinction was not a single event with a single cause. It was a series of overlapping chemical stresses, acidification, deoxygenation, heat, each of which alone would have been survivable, and all of which together became lethal. The survivors were not the strongest, or the fastest, or the most numerous. They were the animals whose body chemistry happened, by evolutionary accident, to cope with the particular combination of stresses the Permian Ocean was now delivering. The ocean was becoming poisonous in more than one way at once. Acidity was dissolving shells, oxygen was disappearing from the water column, and beneath all of it, in the deep layers that no sunlight had reached for millions of years, something else was starting to move. Something that had been waiting patiently for conditions like these to return to the Earth. The deep ocean in an ordinary world is not still. It is slow, but it is not still. A parcel of water that sinks off the coast of Greenland today will travel along the bottom of the Atlantic for centuries, drift past the Cape of Good Hope, cross the Indian Ocean at depth, rise somewhere in the North Pacific, and eventually come back to the surface roughly 1,000 years after it first went under. This immense, looping circulation, what oceanographers call the thermohaline circulation, is the planet's plumbing system. It carries heat from the equator to the poles, it ventilates the deep sea with oxygen picked up at the surface, and it keeps the different layers of the ocean connected, mixing the waters slowly but continuously, so that no single layer becomes isolated from the others. The circulation works because of density. Cold water is denser than warm water. Salty water is denser than fresh water. At high latitudes where the surface cools and ice forms and salt is concentrated in the remaining liquid, the water becomes dense enough to sink. It slides down along the seafloor, pushed by the weight of more dense water forming behind it, and starts its 1,000-year journey through the dark. When the engine runs, the ocean breathes. When the engine slows, the ocean stops breathing properly. And in the late Permian, the engine was slowing. The physics of why is almost embarrassingly simple. Warm the whole ocean, and the surface waters remain warm. Warm the polar latitudes, and the temperature difference between the poles and the tropics shrinks. Shrink that difference, and the surface water at the poles no longer gets cold enough to sink. Without that sinking, the whole circulation weakens because nothing is pushing water down into the depths anymore. And once the circulation weakens, the depths stop receiving the oxygen that surface waters would normally deliver to them. Over something like 50,000 years, this is what happened across the Permian world ocean. The surface kept its oxygen more or less because wind and waves still mixed air into the upper layers. But below a certain depth, a depth that varied from place to place but generally lay somewhere in the middle of the water column, oxygen levels began to fall. Not everywhere at once, in pockets first, in basins where the water was already poorly circulated, in the shadow of continental shelves, in the bottoms of ancient troughs. Then the pockets grew, then the pockets merged, and by the time of the main extinction pulse, most of the deep ocean had entered a state that marine chemists call anoxic, meaning, essentially, that there was no oxygen left in it at all. Uranium isotopes, locked into limestone sediments laid down during these events, tell the story with unusual precision. Uranium behaves differently in oxygenated water than it does in water without oxygen, and the ratio of two of its isotopes gets recorded permanently in the calcium carbonate that forms on the sea floor. When researchers read those isotopes across the Permian-Triassic boundary, what they see is a sharp global shift toward deoxygenated conditions at precisely the moment the marine extinction peaks. The ocean is not losing its oxygen gradually through the long, late Permian. It is losing it quickly in a geological instant. At the same moment, the reefs are collapsing and the shells are dissolving. And this matters because an anoxic ocean is not merely an ocean without fish. It is an ocean in which the chemistry of the water itself begins to change. Most of the organisms you can see in a modern ocean are aerobic. They use oxygen, they produce carbon dioxide, they run the chemistry that dominates the living surface of the planet. But oxygen-breathing life is, in evolutionary terms, a relatively recent invention. Before it existed, in the deep past of the Earth, more than 2 billion years ago, the world's microbial communities ran on different chemistry entirely. They used sulfate instead of oxygen. They breathed, if you can call it that, by reducing sulfate compounds in the water to hydrogen sulfide. And they produced, as a metabolic waste product, vast quantities of that gas. Those microbes never went extinct. They were outcompeted. When oxygen filled the oceans and atmosphere of the early Earth, the aerobic organisms took over most of the habitable space, and the sulfate reducers were pushed into margins, into deep sediments, into stagnant basins, into the few places where oxygen did not reach. They have been waiting there patiently for 2 billion years. The chemistry they practice is not forgotten, it is dormant. When the deep Permian Ocean lost its oxygen, the sulfate reducers woke up. This is not a metaphor, it is a straightforward ecological fact. In any deep-sea basin where oxygen disappeared, sulfate-reducing bacteria began multiplying. They consumed organic matter raining down from the surface, they pulled sulfate out of the surrounding seawater, and they released hydrogen sulfide into the water as a waste product. In small quantities, in poorly circulated corners of a normal ocean, this process happens all the time. The Black Sea today is a minor example of it. But in the Permian, the conditions for this chemistry were not confined to corners. They had taken over much of the deep ocean, and the hydrogen sulfide, having nowhere to go, began to accumulate. For a while, the problem was confined to the depths. A layer of oxygenated water at the surface kept the hydrogen sulfide trapped below, because oxygen and hydrogen sulfide react on contact, destroying each other. As long as the surface was still breathing, the gas could not rise. But the surface was getting warmer. The warmer it got, the less oxygen it could hold. And the boundary between the oxygenated upper layer and the toxic lower layer, what oceanographers call the chemocline, began to drift upward. What this meant for the animals still alive in the Permian Ocean was something with no real modern analogue. The deep sea was uninhabitable by any aerobic organism. The surface was so warm that tropical waters were approaching temperatures at which fish physiology simply fails. Between these two zones, a shrinking habitable band of water, cool enough to breathe in, oxygenated enough to breathe at all, was being squeezed from above and below. Fish that lived in the deeper portions of that band had nowhere to descend because the depths were lethal. Fish that lived nearer the surface had nowhere to rise because the surface was cooking. Entire populations were being compressed into narrower and narrower vertical ranges, competing for the same dwindling middle layer. If you had been able to drop a camera into the Tethys Sea at the height of the crisis, you would have seen the compression visibly. Schools of small fish, mollusk larvae, zooplankton, all crowded into a band maybe 50 meters thick, sometimes less. Above them, water too hot and too thin on oxygen to sustain them. Below them, water in which the very chemistry was wrong, where nothing aerobic could function. And permeating everything, the slow, patient rise of sulfidic water from below, pushing the habitable zone thinner every decade. Most of them did not die of starvation. They did not die of predation. They died, for lack of a more precise word, of suffocation, caught in a narrowing corridor between two forms of ocean that had both become uninhabitable, with nowhere left to go. And what was building up in the deep water, out of sight of any living fish, was a reservoir of poison that had been growing for thousands of years. It was not stable there. It was under pressure, chemically speaking, and pressure has a way of finding release. The chemocline was drifting upward. The surface was getting thinner. And in certain places, in shallow basins, in warm gulfs, along coastlines where the oxygenated layer was shallowest, the boundary was already close to breaking. When it broke, the ocean would change color. In a shallow gulf, somewhere along the coast of Pangaea, 252 million years ago, a morning broke over water that no longer looked like water. The sea was not blue. It was not grey. It was something between pale green and milky white, a colour no modern ocean has ever worn, and it carried a smell that would have been instantly recognisable to any human unfortunate enough to be standing on the beach. The smell of rotting eggs, the smell of a struck match. the smell of hydrogen sulfide rising off the surface of a sea that had, in the last few decades of its life, begun to exhale a gas that the planet had not tasted in 2 billion years. To understand why the ocean changed color, we need to go back to what was happening beneath it, because the transformation was not sudden in the sense of being spontaneous. It had been building for a long time, layer by layer, as the deep sea accumulated hydrogen sulfide and the surface layer of oxygenated water grew thinner. The boundary between the two, the chemocline, had been drifting upward, not fast in any ordinary sense, but steadily, decade after decade, century after century. And a boundary like that, once it begins to move, becomes progressively less stable. In 2005, 3 researchers, Lee Kump, Alexander Pavlov, and Michael Arthur, working at Penn State, published a paper that proposed a specific mechanism for what happened next. It is still the dominant hypothesis for the marine kill of the Great Dying, and it is worth following carefully because it demonstrates how a simple shift in ocean chemistry can become, in the right conditions, a global disaster. Hydrogen sulfide in seawater is not permanent. It reacts with oxygen rapidly whenever the two meet. As long as there is an oxygenated surface layer above a sulfidic deep layer, the boundary between them acts as a kind of chemical fence. The sulfide cannot rise past it, because any molecule that tries is destroyed on contact with dissolved oxygen. But the fence is only as strong as the oxygen behind it. If the oxygenated layer thins enough, or if the sulfide concentration below rises high enough, the reaction zone cannot keep up. A pocket of sulfide breaks through, and once it does, the dynamics shift catastrophically, because sulfide that has escaped the depths now sits in water where photosynthetic organisms can reach it. This is where a particular group of bacteria enters the story, an ancient lineage called the green sulfur bacteria, or chlorobiaceae. They are not plants, they are not algae, they are photosynthetic microbes, but they do something that no plant on Earth can do. They run photosynthesis without oxygen. Instead of using water as their hydrogen source the way plants do, they use hydrogen sulfide, and instead of releasing oxygen as a waste product, they release elemental sulfur. For 2 billion years, these bacteria have lived in the margins of the living world, confined to deep lakes, stagnant bogs, the bottoms of poorly circulated basins, anywhere that sunlight could reach, but oxygen could not. They are a living fossil of what photosynthesis looked like before the oxygen revolution, and they have been waiting in their small corners for an opportunity. The late Permian gave them one. When hydrogen sulfide breached the oxygenated surface layer of the Tethys and the shallow Panthalassan seas, the green sulfur bacteria found themselves in an environment they had not experienced on a global scale in hundreds of millions of years. Sunlit water full of their preferred chemistry. They bloomed. They bloomed at a scale modern oceans have no comparison for. Across vast stretches of tropical coastline, the surface waters turned green-white with their pigments, a color that would have been visible from altitude if anything had been flying. The rocks of the period preserve the evidence directly. Scientists working on sedimentary cores from the Permian-Triassic boundary have identified the biomarkers of green sulfur bacteria, specific organic molecules that only these bacteria produce, in rocks from Australia, from China, from the Arabian Peninsula, from nearly every location where shallow marine sediment survived the extinction. The bloom was not a local event. It was a planetary one. And the blooming bacteria were not the only problem. They were the visible part of a process that was now running away. Once sulfide was reaching the photic zone, more of it was being produced. The green sulfur bacteria themselves did not produce hydrogen sulfide. They consumed it, but their activity stabilized an ecosystem in which oxygen could not re-establish itself. The surface layer that had been keeping the deep poison contained was not simply thinning anymore. It was being replaced. In place of an oxygen-based surface ocean, a sulfide-based one was forming, kilometers wide, meters deep, growing. And unlike the deep sulfide reservoir, which had been insulated from the atmosphere for thousands of years, this new surface sulfide was in direct contact with the air. Hydrogen sulfide is not a stable gas at the ocean-atmosphere interface. It outgasses. Any body of water containing dissolved hydrogen sulfide will release it to the air above, steadily, at a rate that depends on concentration and temperature. When Kump and his colleagues calculated how much hydrogen sulfide a green water Tethys Sea would have released into the Permian atmosphere, the number they arrived at was staggering. Over 2,000 times the modern flux from volcanic sources. More than the entire planet's sulfur output today, coming from the oceans alone every year for as long as the euxinic conditions persisted. This is where the kill mechanism becomes specific. 1,000 parts per million of hydrogen sulfide in air is lethal to most vertebrates within minutes. 100 parts per million will kill a human being over the course of a long exposure. Even 10 parts per million causes significant respiratory damage. The coastlines of the late Permian, where the green seas met the hot continents, were developing concentrations of atmospheric hydrogen sulfide that no land animal could breathe through for long. A gorgonopsid drinking from a tidal pool, a dicynodont browsing in the coastal scrub, a small cynodont hunting insects near the shore. Each of them was walking into a chemistry that its lungs had no protection against, and there was no evolutionary history of selection to protect them, because nothing had needed to survive these conditions in 2 billion years. Away from the coasts, the effect was less immediate. But hydrogen sulfide, once in the atmosphere, does not simply stay near the ground. It rises, it mixes. In high enough concentrations, it travels on wind patterns, drifts inland, reaches ecosystems that were never near the poisoned seas in the first place, and at altitude in the upper atmosphere, it encounters the ozone layer and begins to react with it in ways the Earth has rarely experienced. The air above the coastline, then, was doing two things at once. It was killing the animals immediately beneath it, and it was beginning to break something higher up, something that the biosphere had come to depend on without ever knowing the dependence was there. The green ocean had, in a sense, climbed out of the water. It was moving into the sky. If you had been standing on a Pangaean coast at the height of the crisis, and no large animal ever stood there for long, you would have seen a sea the color of milk mixed with algae. You would have heard waves that sounded normal because the physics of water did not care about the chemistry. You would have smelled the sulfide before you felt it in your lungs. And above you, the sky would have looked almost right, slightly hazy, slightly wrong in a way you could not name. The sun would have felt stronger than it should have, at that angle, at that time of day. The shield was thinning, not the one you could see, the one you could not. 30 kilometers above the surface of the Earth, in the cold, thin air of the stratosphere, there is a layer of ozone that makes the planet habitable for anything with exposed tissue. The layer is not thick. If you could compress it to the density of the air at sea level, it would be about 3 millimeters deep, the width of 2 credit cards stacked together. That entire 3 millimeters spread around the entire planet absorbs most of the ultraviolet radiation that the sun delivers to the upper atmosphere. Without it, the wavelengths of light that reach the ground would break chemical bonds in skin and leaves and pollen. Life could still exist on Earth. It could not exist on the land surface, at least not in any form recognizable today. The ozone layer has been there, more or less continuously, for hundreds of millions of years. It was one of the enabling conditions for plants to colonize the continents in the first place. And in the late Permian, it started coming apart. The chemistry of ozone destruction is a story most people already know in broad outline, because humans in the 20th century nearly replicated it by accident. Chlorofluorocarbons, the compounds once used in refrigerators and aerosol cans, drift up into the stratosphere, where ultraviolet light breaks them apart and releases chlorine atoms. A single chlorine atom, once freed, can catalyze the destruction of tens of thousands of ozone molecules before it is eventually removed from the system. The reaction is not a consumption, it is a catalysis. One halogen atom, operating at stratospheric altitudes, is a small industrial plant for the manufacture of holes in the sky. In the Permian, the source of those halogens was not refrigerators. It was Siberia. Beneath the Siberian traps, buried in the thick sedimentary layers that the intruding sills were cooking, lay enormous beds of evaporate salt, Cambrian-age deposits that had accumulated when ancient seas dried up hundreds of millions of years earlier. Modern experiments have shown that when these same rocks are heated in the laboratory, they release methyl chloride and methyl bromide in high concentrations. Methyl bromide in particular is a potent ozone destroyer, catalyzing the breakdown of the stratospheric layer far more efficiently, molecule for molecule, than chlorine. And the Siberian magma was doing at planetary scale exactly what the laboratory experiment does at laboratory scale. Every sill that pushed into an evaporate deposit cooked out more of these compounds. Over thousands of years, they accumulated in the troposphere, and from the troposphere, a fraction of them escaped upward into the cold, stable air of the stratosphere, where ozone chemistry had no defense against them. There is a second piece to this mechanism, and it was worked out in detail by a separate research team in 2007. Hydrogen sulfide, rising off the green seas, does not normally reach the stratosphere. It reacts too quickly with atmospheric hydroxyl radicals to travel far from its source. But that reactivity cuts both ways. When hydrogen sulfide floods the troposphere in the quantities the Permian oceans were producing, it consumes the hydroxyl radicals that would normally cleanse the lower atmosphere of other compounds. Methane, in particular. With the hydroxyl reduced, methane concentrations rise, and methane, unlike hydrogen sulfide, does reach the stratosphere, where it reacts with the halogens that were already eroding the ozone layer and accelerates the destruction further. The result, in global atmospheric models, is a stratosphere under multiple simultaneous attacks. Halogens from Siberian evaporates, elevated methane from the crippled troposphere. And behind both, the simple fact that an atmosphere in this much chemical disarray could no longer hold its upper defenses together. Depending on which model you run and with what parameters, the ozone depletion during the Great Dying ranges from severe regional thinning to something close to complete global collapse. Either way, the ultraviolet light reaching the ground rose dramatically, not gradually, across a long trend. Across a geologically short window, tens of thousands of years at most, the sky over Pangaea stopped filtering the sun. How we know this is the part of the story that matters most, because the evidence is preserved in something small and almost trivial looking. Pollen grains. Every pollen grain produced by a modern plant comes coated in a set of chemical compounds that function as sunscreen. These are called UV-absorbing compounds, and their job is to protect the reproductive cells inside the pollen from the ultraviolet light the plant cannot control. Plants adjust these compounds dynamically. When ambient UV is high, they load more of them into the pollen wall. When ambient UV is low, they load less. A pollen grain, in other words, is a little environmental sensor recording the ultraviolet conditions its parent plant experienced. And the compounds, once deposited, can survive in fossil form for hundreds of millions of years. In 2023, a team led by Feng Liu at the Nanjing Institute of Geology and Paleontology published the results of an analysis of roughly 800 pollen grains from a Permian-Triassic boundary section in Tibet. What they found was a sharp spike in the concentration of UV-absorbing compounds at exactly the moment of the extinction. The plants that produced those grains had sensed an atmosphere flooded with ultraviolet light and responded by trying to protect themselves. In many cases, the protection was not enough. Alongside the UV-absorbing spike, the team documented a surge in malformed pollen, grains with the wrong number of apertures, asymmetrical structures, tetrads that failed to separate properly. These deformities are the classical signatures of ultraviolet damage during pollen formation. They are, in a certain sense, fossilized mutations. The malformations were not confined to Tibet. Similar abnormal pollen assemblages have been identified in rocks of the same age from the Arctic, from Greenland, from Europe, from Australia, from the southern tip of South America. Wherever the Permian-Triassic boundary preserves well-resolved pollen, the pattern is the same. A world in which plants were, in a very literal sense, being sunburned to the point of sterility. What this meant for the forests that had not already collapsed was a secondary kill. A plant can survive many things. It can tolerate drought, at least for a while. It can tolerate heat. It can even tolerate elevated carbon dioxide, but if its pollen cannot complete meiosis, if the reproductive cells cannot divide properly because the DNA keeps being damaged by ultraviolet light, then the plant cannot reproduce. The individuals already alive will live out their natural lifespans, but there will be no next generation. Forests that survived the drought pulses, the flooding, the acidification, the atmospheric sulfide could still be finished off by the simple failure of their reproductive cycles. And over tens of thousands of years, many of them were. There is something strange about this particular mechanism, which is worth sitting with for a moment. Most of the kill mechanisms of the Great Dying were dramatic in their immediate effect. Drought killed forests in years. Hydrogen sulfide killed coastal animals in hours. Ocean acidification killed shelled life over centuries. The ultraviolet kill was slower than any of them, and in some ways more insidious. It did not strike down the generation that experienced it. It struck down the generation that would have come after. An organism under ultraviolet stress could look, to any casual observer, completely healthy. It was only at the level of the reproductive cells, invisible to the naked eye, that the damage accumulated. The ecosystem was not being murdered, it was being sterilized. And this, layered on top of everything else that was happening, is why the recovery took so long. A damaged ecosystem with intact reproductive capacity can rebuild itself. A damaged ecosystem whose reproductive cells have been shredded by atmospheric radiation cannot. Not on any short timescale. Not while the ultraviolet flux remains elevated. Not while the ozone layer remains thin. The forests of the Permian were not only being killed, they were being prevented from returning. Overhead, the sky continued to do what an atmosphere does when it has lost its upper defenses. The blue of the daytime remained blue because the wavelengths that cause atmospheric scattering were not the ones affected. The sun looked unchanged. A late Permian afternoon, seen by any organism with functional eyes, would have looked entirely normal. It was only the chemistry that had shifted, and chemistry does not announce itself. The ultraviolet radiation falling on the leaves and the pollen and the skin of every exposed animal was higher than any organism on the planet had been evolved to tolerate. There was no alarm. There was no sound. The damage simply accumulated year by year in the cells that would have built the next version of the world. Every animal that has ever lived has a thermal ceiling, a temperature above which its own biochemistry stops working. For most vertebrates, the ceiling is somewhere between 40 and 45 degrees Celsius in the body's internal temperature, because above that, the proteins that do the work of keeping a cell alive begin to unfold. Enzymes lose their shape, cell membranes become leaky, oxygen delivery to tissues fails. The animal has no way to repair the damage fast enough, and within a window measured in minutes to hours, depending on the species and the conditions, it simply stops being an animal and becomes a body. The ceiling is not something an organism can negotiate with. It is a fact of biochemistry, as fixed as gravity, and it has remained essentially unchanged across hundreds of millions of years of evolution. A late Permian decinodont had roughly the same thermal ceiling as a modern cow. A gorgonopsid had roughly the same as a modern hyena. And when the air around them reaches temperatures high enough to push their core body temperature past that ceiling, they die. Not slowly, not with any sense of approaching danger, but in the space of a single bad afternoon. The question then is what temperatures the Permian world actually reached. For a long time, the answer was uncertain. Paleoclimatologists could estimate broad averages. They could point to isotope anomalies, to sediment types, to the presence or absence of certain fossils, and argue that the late Permian had been hot. But how hot was difficult to say with any precision, because the available climate models made an assumption that turned out to be wrong. The assumption was that sea surface temperatures could not, physically, exceed about 30 degrees Celsius. The reasoning was solid as far as it went. Warm surface water evaporates rapidly, and evaporation cools the water down. In any climate modelled by conventional physics, tropical oceans should have been self-regulating, capped at around 30 degrees, no matter how much carbon dioxide the atmosphere held. In 2012, a team led by Yadong Sun, the same researcher who would later publish the Mega El Niño findings, showed that the assumption was wrong. Sun and his colleagues collected something on the order of 15,000 conodont teeth from a series of rock sections in southern China, covering the interval from the late Permian through the early Triassic with unusual completeness. Those teeth had formed in the mouths of small eel-like creatures living in tropical Tethys shelf waters, at different points across hundreds of thousands of years. And the oxygen isotopes preserved in their mineralized bodies allowed the team to reconstruct the temperature of the water each animal had lived in, not as an average, not as a rough estimate, as a direct thermometric record, one tooth at a time, across the entire extinction interval. What they found was that tropical sea surface temperatures during the early Triassic climbed to around 40 degrees Celsius. Not briefly, not as a regional anomaly, as a sustained state over millions of years across the equatorial ocean, a value that no prior model had considered physically possible, written into 15,000 independent isotope measurements. Paul Wignall, who co-authored the paper, put it plainly when the results were published. Nobody had ever dared say that past climates attained these levels of heat, he said, and the implication of the data was that our climate models had been underestimating what a stressed tropical ocean could do. 40 degrees is near the thermal threshold of marine life itself. Above that, most fish cannot extract enough oxygen from the water to meet their metabolic needs, because warm water holds little dissolved oxygen and a fish's gills can only work so hard. Photosynthetic plankton, the base of the entire marine food web, begin to fail. Coral species, even the hardiest modern ones, bleach and die. At 40 degrees, a tropical ocean is not merely hot, it is beyond the tolerance of any complex ecosystem that has ever been described, and the early Triassic held that temperature at the equator for somewhere around 5 million years. Ocean temperatures translate, roughly, into land temperatures in predictable ways. The continents of Pangaea, which baked under the same sun that was warming the seas, reached peak temperatures far higher than the oceans did. Climate modeling based on Sun's data suggests that tropical land surfaces during the worst intervals of the early Triassic may have approached 50 to 60 degrees Celsius during the hottest months, not in localized deserts, across enormous stretches of the continental interior. At those temperatures, an exposed animal's body cannot shed heat fast enough to survive, regardless of how much water it has access to. Evaporative cooling, the mechanism that keeps modern mammals alive in hot climates, stops working when the air itself is too hot to accept moisture efficiently. A creature with fur, fat, and a high metabolic rate, the ancestors of mammals, the dominant terrestrial vertebrates of the late Permian, simply cannot function in that environment. The result was a pattern that paleontologists now describe as the tetrapod gap. Across the early Triassic, the fossil record shows an almost complete absence of land vertebrates between roughly 30 degrees north and 40 degrees south of the equator. Not reduced diversity. Absence. For a band of latitude that stretches roughly from modern Cairo to modern Buenos Aires, covering the warmest zones of the planet, there are essentially no land animals of any size in the fossil record for several million years. They had either died where they lived or retreated toward the poles, and in either case, the equator was no longer theirs. If you could walk through this world, and no vertebrate, ancestral or otherwise, walked through it for long, you would find a landscape so strange that your modern sense of what a planet should look like would fail to process it. Knee-high scrub vegetation, mostly lycopsids, covering ground that had once held 30-meter rainforest canopies. No trees, no forests, no shade. The wind would move across that vegetation and produce a single sound, a low, dry rustle repeated to the horizon. You would see no movement other than the vegetation itself. No birds, because birds were still 200 million years in the future. No mammals, because mammals had not yet evolved. No reptiles of any notable size, because the heat had killed them. The only sound beyond the wind would be insects, the tougher kinds, beetles, cockroaches, the dragonfly families that could exploit seasonal wet intervals. And even they would be thinner than they had been in the Permian, reduced in species count by an order of magnitude. The ground underfoot would be hot, not uncomfortable in the way a hot beach is uncomfortable. Hot in the way a cast iron pan left in the sun is hot, hot in a way that touches your feet through whatever you are wearing. The air would shimmer above it. The sky would be hazy, washed out rather than blue, and the sun directly overhead would feel heavier than any sun you have ever stood beneath. A human body placed in that environment, without shade or active cooling, would be in serious trouble within an hour. Any native animal would already have moved, generations ago, either to the cooler margins of the continents or out of existence altogether. The tropics had not ceased to receive sunlight. They had not ceased to receive rain, at least in the wet phases of the lingering El Niño cycles. What they had ceased to be was habitable, and the inhabitation, once lost, did not return quickly. For the entire 5 million years of the early Triassic super greenhouse, the equatorial zone of the Earth remained a dead band, populated by stress-tolerant plants and small opportunistic invertebrates, and essentially nothing else. The temperate latitudes, meanwhile, the parts of Pangaea that lay closer to the poles, were warm but not lethal. A few pockets of survivors were making their way through the crisis there, in climates that had become tropical but not yet incinerating. These refugia were small. They were scattered. They held the future of terrestrial vertebrate life inside them, and they did not know they were holding anything. But they were. And some of what they held would, in time, become everything. Mass extinctions do not, as a rule, select for excellence. They select for a narrow and sometimes unglamorous set of traits that happen by evolutionary coincidence to match the specific conditions of the collapse. An animal could be elegantly designed, superbly adapted to its Permian niche, at the top of its food web for millions of years, and still be erased completely because none of those virtues mattered to the new chemistry of a warmer, more acidic, less oxygenated world. The survivors of the Great Dying were not the best of the Permian biosphere. They were the ones whose biology, by accident, was compatible with what came next. This is worth holding on to, because the list of who made it through and who did not can seem, at first glance, almost random. Brachiopods, which had dominated the sea floor for hundreds of millions of years, were nearly eliminated. Mollusks, which had been a secondary presence in Paleozoic seas, walked out of the extinction and took over. Among the land vertebrates, the gorgonopsids, the great saber-toothed predators of the late Permian, vanished entirely. The dicynodonts, their herbivorous prey, were almost wiped out too, but one small branch of the group, a pig-sized burrowing animal called Lystrosaurus, came through in numbers large enough to dominate the early Triassic in a way that is unusual even in the fossil record. There is no obvious reason, looking at a Permian ecosystem, that Lystrosaurus should have been the one to inherit the world. And yet it did. Some of the selection becomes explicable once you look at the biochemistry, which is where the 2024 work by Haijun Song and his team turned out to matter so much. The story of hemoglobin and hemocyanin and hemerythrin, the three major families of oxygen-carrying molecules that different animal lineages evolved, is also a story about who could cope with an ocean running low on dissolved oxygen. The mollusks with hemocyanin in their blood could extract enough oxygen from water that held very little of it. The brachiopods with hemerythrin could not. This is not the only reason the two groups diverged across the extinction boundary, but it is a large part of it. When the oceans suffocated, the animals whose blood chemistry had been built hundreds of millions of years earlier for high-efficiency oxygen delivery kept functioning. The animals whose blood chemistry had been built for ordinary conditions did not. The pattern extended beyond mollusks and brachiopods. Across many lineages of marine invertebrates, the species that survived were the ones with higher metabolic flexibility, smaller body size, faster reproductive cycles, and, crucially, an ability to tolerate warm, low-oxygen water. The Permian had been full of large, specialized, slow-reproducing species occupying stable niches. The early Triassic was populated by small, generalist, fast-reproducing species that could thrive in conditions no complex ecosystem had ever been asked to tolerate. The switch was not gradual. It was the result of one group being deleted and another group filling the empty space, and the filling happened fast once the empty space opened up. On land, Lystrosaurus was the clearest example of how this played out. A modern visitor to the Karoo Basin of South Africa can walk through the same sedimentary layers that preserved the transition, and the shift in fossil abundance is visible even to someone who has never studied paleontology before. Below the extinction horizon, the rocks hold a diverse assemblage. Dozens of species of synapsids, a handful of different parareptiles, various small archosauromorphs, insects, amphibians. Above the extinction horizon, in the earliest Triassic layers, that diversity is almost gone. In some sections, Lystrosaurus fossils make up as much as 90% of all land vertebrate remains. It is not an exaggeration to say that the early Triassic landscape on some continents had one medium-sized animal on it in large numbers and very little else. Why Lystrosaurus specifically is a question that paleontologists are still sorting out. Some of the reasons are clearly visible in its biology. It grew fast, reaching reproductive age quickly, which meant it could sustain population even when life expectancy collapsed. It bred in groups, which gave its young protection they might not have had individually. It burrowed, which allowed it to escape the worst of the daily heat extremes that were now killing surface-dwelling animals. And it was, by some evidence, a resilient traveller. Fossils identifying the same genus turn up in southern Africa, in India, in Russia, in Antarctica, in parts of what is now China. When almost every other vertebrate lineage was being compressed into shrinking refugia, Lystrosaurus was spreading. There is also the possibility, which researchers now take seriously, that Antarctica served as a specific refuge during the worst of the crisis. The southern polar regions of Pangaea, while still warmer than any modern polar zone, remained cool enough to avoid the lethal heat that was sterilizing the tropics. A population of dicynodonts that had been sheltering there during the extinction's peak would have found, when the worst passed, that the entire continent was available to them. They spread outward from that sanctuary, and because they were spreading into an empty world, nothing resisted the spread. This produced a phenomenon that, until recently, paleontologists found difficult to explain. For several million years after the extinction, the same handful of species shows up as fossils all over the planet. A site in what is now Russia and a site in what is now South Africa contain, in many cases, the same animals. The normal pattern of biological diversity, different species in different regions, ecosystems shaped by local conditions, had disappeared. The earliest Triassic world was strangely uniform, a planet on which geography had briefly stopped producing variety. A team led by Jude Al-Aswad at Stanford, working through the End Permian marine fossil record in 2025, argued that this homogenization was not really an ecological mystery at all. It was a climate consequence. When the tropics become uninhabitable, the animals that can survive the surrounding conditions expand into the habitable bands on either side, and those bands, regardless of where they are on the map, offer similar enough environments that the same species can occupy them. What looks like a breakdown of biogeography is actually a contraction of habitat. The entire planet, during the recovery, was running on a narrower range of physical conditions, and fewer conditions means fewer niches, and fewer niches means fewer species filling the world more uniformly. The life that survived was stranger than just low diversity. For a brief window near the extinction horizon, the fossil record registers what is called the fungal spike, a planet-wide surge in fungal spores and filaments preserved in sediments across continents. Fungi, unlike animals or plants, do not need to photosynthesize and do not need to breathe in the way complex life does. They decompose. They feed on dead matter. And the late Permian gave them an abundance of dead matter unlike anything the planet had seen before. For tens of thousands of years, the terrestrial world may have been dominated, in biomass terms, not by surviving animals or struggling plants, but by the fungal networks consuming everything the extinction had left behind. Forests that had been living ecosystems for millions of years became, for a while, substrate. If you had walked across what is now the Karoo Basin in the earliest Triassic, you would have seen a landscape that had stopped being lush without yet becoming empty. The vegetation was sparse but present, small lycopsids and stress-tolerant ferns clinging to damp, low-lying areas. The air was warmer than Permian air had been, but not yet at the lethal extremes that would come in a few 100,000 years. And scattered across the landscape, wherever you looked, you would see the same animal. Stocky bodies, barrel chests, short legs, the twin, downward-curving tusks that identified their lineage. Dozens of them in a group, sometimes hundreds. Lystrosaurus, in numbers that no modern large animal sustains, moving together across a world that had almost nothing else moving in it. They were not particularly clever. They were not particularly fast. They were not particularly beautiful by any standard their more spectacular Permian relatives had set. But they were alive, and the gorgonopsids were not, and the brachiopod reefs were not, and the giant Gigantopterous forests were not. And from their lineage, through the small cynodonts sheltering in burrows alongside them, through 50 million years of slow diversification, would eventually come the animals that built themselves warm blood and fur and placentas, and from those animals, eventually, would come the one that is listening to this voice right now. Your ancestors came through the great dying looking like that, small, unimpressive, burrowing, living in groups on a ruined continent. There was nothing about them in 252 million years ago that would have suggested what their descendants would become. But they kept going, and that, in the end, was enough. When an ecosystem collapses, the expectation is that it will rebuild. This is the pattern the planet has followed after every previous crisis in its long history. Small animals diversify into the empty niches left by the dead. Plants recolonize the scarred landscapes. Reefs regrow on the seabed, slowly at first, then with gathering speed, and within a few 100,000 years, what had been a wounded world is a world again. This is the normal rhythm of extinction and recovery. It is the rhythm that came after the end Ordovician collapse. It came after the late Devonian die-off. It would come again 186 million years later, after the asteroid that ended the dinosaurs. It did not come after the Great Dying, not for a very long time. The fossil record across the early Triassic is one of the strangest stretches of rock on Earth, because it documents an ecosystem that refused to restart. For about 5 million years after the extinction, the planet held itself in a state that paleontologists struggled for decades to name properly. Some called it a dead zone. Others called it a disaster interval. The most recent research, published by Zhen Zhu and her colleagues in 2025, calls it what it physically was: a super greenhouse locked in place by the loss of the tropical forests that would normally have cooled it. The logic of the lock is simple once you see it, and it is worth walking through carefully, because it explains why the Great Dying remains a unique event in the geological record. A healthy forest draws carbon dioxide out of the atmosphere and stores it through photosynthesis in living wood and roots and soil. When the Permian tropical forests collapsed, that drawdown stopped. Carbon dioxide emitted by the already dying Siberian traps kept accumulating in the air, because nothing on land was pulling it back out at the rate a forest would have. With elevated carbon dioxide came elevated temperatures. With elevated temperatures came conditions in which forests could not re-establish themselves, and without forests, the carbon dioxide could not be pulled back down. This is what systems analysts call a runaway loop. Every input amplifies itself, every output reinforces the cause, and the system does not return to its previous state on any timescale a complex organism would recognize as meaningful. The early Triassic was not a slow recovery. It was a steady state, new and stable and hostile, that the planet had found for itself and could not easily leave. For about 5 million years, the surface of the Earth simply held. Not improving, not degrading further, holding. And 5 million years is not a figure of speech. It is longer than the entire evolutionary history of the genus Homo. It is roughly 20 times the span of time from the last glacial maximum to the present day. If a human civilization had arisen at the beginning of the early Triassic super greenhouse and maintained continuous occupation of the Earth through its end, that civilization would have outlasted every empire in our species' experience by more than 1,000 times over. It is a timescale that breaks ordinary intuition. The planet sat in its broken configuration for a length of time so long that evolution, working on most lineages, could not keep pace with the conditions because the conditions were not changing. What life there was during that interval kept going in reduced form. The shallow seas held their mollusk faunas, which diversified cautiously from the small number of genera that had survived. The continental margins held Lystrosaurus populations, gradually giving way over hundreds of thousands of years, to a slightly wider assemblage of therapsids and early archosauromorphs. A few pioneer species of insects continued their work. Fungi did what fungi do, breaking down the debris of an ecosystem that had not yet learned how to be alive again. But there were no large vertebrates in the tropics. There were no tall forests anywhere. There were no reefs, in the sense that the Permian had known reefs. The animals and plants that composed early Triassic ecosystems were a shadow cast by what had come before, waiting for conditions that would not improve for longer than anyone thinks about time. One way to feel the length of the silence is to try to imagine it. If you had walked across the interior of Pangaea somewhere in the middle of the early Triassic, say 2 million years after the extinction, you would have found a landscape that had not changed significantly since the collapse. The vegetation was still sparse and low. The soil was still thin and eroding. The air was still hot and held more carbon dioxide than any air you have ever breathed. Somewhere in the distance, small groups of Dicynodont descendants still moved across the open ground in the way Lystrosaurus had moved, though the species had shifted and the animals were a little different now. In the sky above, the sun was still unshielded in a way that would have damaged unprotected tissue on long exposure, though the pollen record suggests the worst of the ultraviolet crisis had eased by this point. The ocean, far to the south, was still warm enough at its surface to kill most modern fish. If you returned to the same spot 100,000 years later, the scene would be almost identical. Return again, another 100,000 years on, and you would see almost the same sky, the same vegetation, the same handful of animal lineages. The planet, which had spent the Permian changing in visible ways across intervals of a few thousand years, had stopped making visible progress. The usual rhythms of biological change were suspended. Something else had replaced them, and that something was not really a rhythm at all. It was a holding pattern. Recovery, when it finally began, did not begin everywhere at once. The temperate latitudes started before the tropics. The oceans recovered slightly ahead of the land. The continental interiors were the last to return to anything resembling biological richness, and the tropical forests, the high canopy, high diversity rainforests of the kind that had dominated the Permian tropics, did not come back during the early Triassic at all. They would not come back in any recognizable form for tens of millions of years. When the first truly diverse Mesozoic forests finally established themselves, they were built by different plant lineages entirely, because the Permian flora had not survived the silence that killed what was left of it after the extinction itself. The animals followed a similar pattern: lacustrine ecosystems. Freshwater food webs in lakes and rivers took about 10 million years to rebuild full trophic complexity. Terrestrial vertebrate communities did not reach pre-extinction levels of species richness until roughly 30 million years after the boundary, by which time the planet had entered the late Triassic and a new set of animal groups was beginning to rise. The first dinosaurs appeared in that recovery interval, descended from small bipedal archosauromorphs that had sheltered on the margins of the early Triassic dead zone. The first true mammals appeared in that recovery interval as well, descended from the small cynodonts that had burrowed alongside Lystrosaurus for generations without notice. None of those future descendants would have been visible to any observer during the long silence itself. The early Triassic was not a preview of the Mesozoic. It was a delay before it, a pause during which the Earth held its breath, so to speak, while a new cast of characters assembled themselves in the wings. If you had been the observer, 2 million years after the boundary, watching small reptiles dart through knee-high vegetation on a warm and empty continent, you would have seen no sign of what those reptiles' descendants would eventually become. Dinosaurs were not visible in early Triassic fossils. Mammals were not visible in early Triassic fossils. Birds, which would not exist for another 150 million years, were not visible in anything at all. The future was encoded in the present, the way the future always is, and it was invisible, the way it always is too. The strangest thing about the long silence is how thoroughly it has been forgotten by public memory. The Great Dying is known, dimly, as a catastrophe. The recovery from it is almost unknown. But the recovery is, in its own way, as important as the catastrophe. It is the period during which the planet's biology reorganized itself at the molecular level, during which the structural winners of the New World, fast-growing, heat-tolerant, reproductively efficient, were selected and diversified. It is the period that set the stage for every vertebrate that has existed since. The Permian is the world we lost. The early Triassic is where the world we have came from. Understanding how any of this is known, given how thoroughly the rocks have weathered and the fossils have fragmented and the chemistry has decayed across 250 million years, is its own story. The evidence for everything in the Great Dying, from the timing of the sill intrusions to the chemistry of the vanished oceans, had to be extracted from rock, piece by piece, over more than a century of work. It is worth spending some time on that extraction because the answer to how we know any of this is the reason we know it at all. There is a hillside in Zhejiang province in southeastern China where the rocks of the end Permian world are exposed in almost perfect sequence. The site is called Meishan, and it is not much to look at. A road cut, a weathered cliff face, a series of grey and brown layers stacked on top of each other in the ordinary way that sedimentary rocks are stacked everywhere on Earth. A tourist driving past would notice nothing remarkable. But those layers are, by international agreement, the global stratotype section and point for the Permian-Triassic boundary, the official reference rock for the most severe extinction event in the history of life. Every question about the timing of the Great Dying, every attempt to correlate what happened in one part of the ancient world with what happened in another, begins, in some sense, at Meishan. Most of what we know about the extinction has been extracted from rocks like these, piece by piece, across more than a century of fieldwork. And the extraction is not a single discipline. It is many disciplines working in parallel, each one reading a different kind of signal from the same stones. The signals are preserved in forms that would have seemed like science fiction to geologists 100 years ago. Ratios of isotopes, variations of a single element heavier or lighter than its standard form, locked into the chemistry of ancient shells and teeth and sediment grains. Trace elements that shift in abundance when the chemistry of the ocean or atmosphere changes. Organic molecules called biomarkers, produced by specific types of microbes that can survive for hundreds of millions of years if the conditions of burial happen to protect them. Each of these is a kind of instrument built by nature and read by technique. None of them reveals the full story on its own. Together, read carefully, they reconstruct it. The most important temperature record comes from conodont teeth. A conodont was a small, eel-shaped marine animal that lived throughout the Paleozoic, and although the soft body is rarely preserved, the teeth, made of a calcium phosphate mineral called apatite, are among the most durable biological structures ever produced. Apatite survives burial, pressure, and hundreds of millions of years of geological time with its chemistry largely intact. And the oxygen atoms inside apatite, at the moment the tooth formed, locked in a ratio of heavy to light isotopes that depended on the temperature of the water the animal was swimming in. Measure that ratio today and you have in effect a thermometer reading from the Permian Sea. The team led by Yadong Sun, working from rock sections in southern China, extracted something on the order of 15,000 of those teeth. Each one had to be collected from its host rock, cleaned, analyzed in a mass spectrometer, and calibrated against the others. The process took years, What came out at the end of it was a temperature curve across the extinction boundary with resolution so fine that individual climate pulses became visible in the data. Without that curve, the modern picture of the early Triassic greenhouse could not exist. With it, for the first time, paleoclimatologists could say with precision what temperatures the tropical oceans had actually reached. A different team, led by Michael Clarkson at the University of Edinburgh, approached the problem from a different direction. They wanted to know what had happened to the chemistry of seawater, not its temperature, but its acidity. For this, they used boron, a trace element incorporated into the shells of brachiopods in a ratio that depends, very sensitively, on the pH of the surrounding water. By measuring boron isotopes in fossil brachiopod shells from different points along the extinction interval, they produced a pH record that showed the collapse of ocean alkalinity in unmistakable terms. The shells themselves had recorded it. The research was to ask the shells the right question. Jen Xu, working across Chinese and British institutions, asked a different question of the land fossil record. She wanted to know what had happened to the tropical forests, and over what area, and how fast. The work required years of fieldwork across China, travelling to sites that in some cases were accessible only by boat or on horseback, mapping fossil plant distributions against sedimentary indicators of climate. What she and her team produced, when the data were eventually assembled, was a set of spatio-temporal maps of plant productivity across the Permian-Triassic boundary, maps that showed for the first time the geography of the forest collapse. Those maps were what allowed Xu and her collaborator Benjamin Mills to model, in 2025, the carbon cycle consequences of the vegetation loss. Without the maps, the model would have been speculation. With them, it became a testable hypothesis, and the hypothesis matched the observed duration of the super greenhouse with unusual precision. At Stanford, a team working under the supervision of Jonathan Payne took a further step. They were interested in the post-extinction world, specifically in why the recovering marine fauna showed such strange biogeographic uniformity, the same genera appearing on opposite sides of a planet that should have produced regional variety. The lead author, a doctoral candidate named Jude Al-Aswad, built a model that combined physiological constraints on marine animals with climate simulation data from the early Triassic and tested whether the fossil patterns could be explained by habitat contraction alone. They could. The model's predictions matched the observed distributions of bivalves and gastropods across the early Triassic, closely enough that Al-Aswad and her colleagues could argue, in a paper published in 2025, that the post-extinction homogenization was not a biological mystery, but a climatic consequence. These are 4 examples, drawn from dozens of similar efforts, of how the picture assembles itself. The timing of the extinction came from uranium-led dating of zircon crystals in volcanic ash layers, work done primarily by Samuel Baring and his students at MIT, refining the dates across decades until the boundary could be located to within 40,000 years. The evidence for ozone depletion came from the UV-absorbing compounds preserved in Tibetan pollen grains, analyzed by Feng Liu and his team at the Nanjing Institute. The fingerprint of Siberian volcanism in the global ocean was traced with remarkable elegance through nickel isotopes measured in sedimentary rocks from the Canadian Arctic, where the isotopic ratios turned out to match volcanic aerosol particles that had settled out of the stratosphere more than 250 million years ago. Mercury anomalies in the rocks of southern China lined up with the pulses of volcanic activity inferred from Siberian zircons. Each of these methods is, considered alone, subject to uncertainty. The conodont temperatures could be biased by the local ecology of the animals. The boron isotope pH record depends on assumptions about the starting chemistry of Permian seawater. The vegetation maps are incomplete, because the fossil record is always incomplete. Any single line of evidence can be challenged by a sufficiently determined skeptic. What makes the modern picture of the Great Dying durable is that the challenges do not hold up across the full body of evidence. The conodonts say the oceans warmed by 8 degrees. The boron says they acidified by half a pH unit. The nickel says the aerosol fallout was Siberian. The zircons say the timing was tens of thousands of years. The pollen says the ozone thinned. The biomarkers say the seas turned sulfidic. No one researcher could have built this picture. It is the product of a globally distributed, multi-generational effort. A structure held up by the overlap of hundreds of independent measurements, each one a small bolt in a large frame. What is striking, looking at the field as a whole, is how much of the recent progress has come from Chinese institutions. The sedimentary record of the Permian-Triassic boundary is preserved with unusual completeness in southern China, and generations of Chinese paleontologists have spent their careers extracting the story from it. Yadong Sun, Zhen Shu, Feng Liu, Haijun Song, Jianqin Yu, and many others, most of the foundational recent work has been done either in or in collaboration with the China University of Geosciences in Wuhan, the Nanjing Institute of Geology and Paleontology, and a small number of allied institutions. The Great Dying was a planetary event, but the rocks that record it most completely happen to lie in one country, and the modern understanding of the event is disproportionately the work of the scientists who grew up walking past those rocks. There is something in this that is worth acknowledging before moving on. The Great Dying, as a scientific object, does not exist in the way a law of physics exists. It is a reconstruction, a story built from rocks by people, refined across decades, tested against new data, revised when older ideas fail. Everything we have been talking about in this series is the current best interpretation of the evidence as it stands in the mid-2020s. In another generation, some of it will be overturned. Some details will be refined. New methods will extract new signals from the same Meishan hillsides that the first generation of geologists mapped by hand. This is not a weakness of the science, it is how science works. The extinction itself is not in doubt. The details, the mechanisms, the timings, the numbers, those are alive, still moving, still being read and reread by people standing on cliff faces with hammers in their hands. And the reason any of it matters now, in the present, the reason the Great Dying is not merely a story about a dead world, but a question about a living one, has to do with how the mechanisms we have just walked through compare to mechanisms running in our own atmosphere, our own oceans, at the current moment, at rates that are in some ways slower than the Permian and in other ways terrifyingly faster. That comparison is where this story comes home. There is a comparison that paleoclimatologists are reluctant to make because it tends to be misunderstood the moment it leaves their mouths. The comparison is between the mechanisms that ran through the late Permian atmosphere and the mechanisms that are running through ours right now. It is not a prediction. It is not a claim that the modern world is on the verge of becoming the Great Dying. It is a structural comparison of two processes, one complete, one ongoing, that share enough features to be genuinely informative and diverge in enough ways that simple extrapolation from one to the other would be misleading. The comparison is worth making carefully because it is the reason this story matters in the present, and because the careful version of it tells us something the loud version cannot. Start with carbon. The Siberian traps released their load into the late Permian atmosphere across roughly 75,000 years, and during that time, carbon dioxide concentrations climbed from around 400 parts per million to around 2,500, 6 times higher, over a span long enough that most species could not register the change within a single generation, but short enough that the biosphere as a whole could not adjust. Human industrial activity, starting with the widespread burning of coal in the 19th century, has raised atmospheric carbon dioxide from around 280 parts per million to roughly 440 today. That is a factor of about 1.5, rather than a factor of 6, and so on first glance, the modern change looks much smaller. The difference is in the timing. The late Permian release took 75,000 years to achieve its full magnitude. The modern release has covered its smaller range in about 250 years. That is a rate difference of something on the order of 300. Per unit of time, modern human carbon emissions are faster than the carbon emissions of the Siberian traps at their worst. Not in total volume. The Permian event produced far more gas over its entire duration, but in the speed at which that gas enters the system. This matters because biological and chemical feedbacks in the Earth system operate on characteristic timescales. Weathering draws down atmospheric carbon dioxide over hundreds of thousands of years. Forests draw it down over centuries. Oceans absorb it over millennia. A release that happens faster than these sinks can respond is a release that accumulates, and accumulation is what produces the tipping behavior that paleoclimatology has documented. A team led by Maura Brunetti, working on climate modeling that compares Permian-Triassic conditions to modern ones, estimated in 2025 that at current rates of carbon emission, modern atmospheric chemistry will reach the levels that triggered the Great Dying in roughly 2,700 years. Not tomorrow, not this century, but on a timescale radically shorter than the Permian's own. Shorter, in fact, by more than an order of magnitude. If the Permian event was the worst release the planet has absorbed in the last 500 million years, the modern release is proceeding faster than that. None of this means the modern world will replicate the Great Dying. Many of the Permian's killing mechanisms depended on conditions that do not currently exist. Pangaea is gone. The modern continental configuration, with oceans threaded through it, produces a more stable climate system than the supercontinent did. The Siberian trap's particular geological accident, magma intruding into coal and salt, has no modern equivalent. Modern industrial emissions, for all their speed, are nowhere near the total volume of Siberian volcanism over its full duration. These differences are real, and they are the reason most paleoclimatologists are careful to say that the comparison is structural, not predictive. But the structure is what matters, because the structure of the Permian cascade depended less on the details of the carbon source than on what happened once the atmosphere started changing. Warming slowed ocean circulation. Warming intensified climate variability. Warming stressed tropical forests. Forests that stopped functioning as carbon sinks amplified the warming. Amplified warming disrupted rainfall patterns further, which stressed the forests further, which further weakened the sink. These feedbacks, warming, circulation, ecosystem collapse, amplification, are not unique to the Permian. They are general features of how a climate system responds to rapid greenhouse gas input. The Permian ran the full sequence because the input was large enough and sustained enough to push every step past its threshold. Modern conditions have not yet run the full sequence. The question is, how many steps of the sequence have already started? The answer for several of them is some. Ocean circulation in the North Atlantic is slowing measurably by about 15% over the past century. Tropical rainfall patterns are shifting, with extended droughts in regions that were historically wet. The El Niño of 2023 and 2024 was the strongest on record, and its duration, while nothing like the Permian Mega El Niño, was longer than most modern cycles. The Amazon basin is losing mass year after year from a combination of deforestation, rising temperatures, and declining rainfall, and models suggest that continued loss past a certain threshold would tip the forest into a savanna state from which it would not easily return. This is not the Gigantopterous collapse. It is a contemporary echo of the same dynamic, operating in a different forest, on a different continent, under different specific conditions, but following the same physical logic. Yadong Sun, who led the conodont research that established the Permian temperature record, made a comment in 2024 that is worth holding on to. When asked about the relationship between the late Permian event and the modern climate crisis, he pointed out that the Earth has seen rapid carbon release before. It has been here. It remembers the pattern. What is different now, he said, is the identity of the agent. In the Permian, the agent was the Siberian traps. This time, the agent is us. That comment is not a prophecy. It is a precise piece of science communication. The planet is currently receiving a carbon injection on a timescale comparable to the worst natural injection in its history, and the injection is coming from human activity rather than geology. Whether the feedbacks cascade to the extent they did in the Permian depends on variables that are not yet fully determined. How much carbon ultimately enters the atmosphere, how rapidly emissions slow, how resilient modern ecosystems turn out to be under combined stress. These are open questions. They are not questions that paleoclimatology can answer, because paleoclimatology only describes what happened. It does not predict what will. What paleoclimatology does establish, and what makes the Great Dying genuinely instructive, rather than alarmist, is the shape of the space in which the modern experiment is running. We now know that oceans can reach 40 degrees at the surface under sustained greenhouse conditions. We now know that tropical forests can collapse and fail to return for 5 million years. We now know that the feedback between forest loss and atmospheric carbon can lock the climate into a new steady state for longer than any mammal species has existed. These are not hypotheticals. They are measurements from a real past event, preserved in rocks, extracted by the scientific work of the last century. They describe a region of the system's behavior, and the modern world is steering toward that region faster than any previous system has. The question of whether we enter the region and how far into it we go is the question the next few generations will answer. Not through paleoclimatology, but through the combined decisions of the species that is currently acting as the geological agent. The Great Dying is, in a certain sense, a manual. It describes what happens when the agent pushes the system too hard, for too long, in the wrong direction. It does not tell us that we will push that way. It tells us what the system will do if we do. The planet has been through this before. It has come out the other side before, carrying different life, reorganizing its biosphere, continuing. The Earth does not need the Permian forests to survive, and it does not need modern forests either. What we are deciding, in this century and the ones immediately to come, is not whether the planet will continue. The planet will continue. What we are deciding is which version of the planet our descendants will inherit, and what role the particular configuration of life we happen to belong to will play in it. That decision is not the subject of this series. It is the context for why the series exists at all. What we set out to do at the beginning of this story was to understand a mechanism, to walk through the cascade of the Great Dying step by step, to see how one thing became another, to watch the ordinary physics of carbon and water and life produce, under the wrong conditions, the worst catastrophe the biosphere has ever recorded. That understanding is the gift paleoclimatology offers. What is done with it is not its job to say. And there is still something unfinished in the story itself, because the Great Dying is not just a catastrophe. It is also the ground from which everything alive today eventually grew. The silence we walked through, the sterile tropics, the low vegetation continents of the early Triassic, those were not empty. Something was moving through them. Something was keeping going, quietly, across millions of years in which almost nothing else was. and from that quiet movement came the entire world we now live in. 30 million years after the extinction, in what is now northern Argentina, a small two-legged animal about the size of a domestic cat was picking its way across a riverbank at dusk. It had long hind legs, a narrow tail, and a pointed snout full of sharp teeth. Its movements were quick and precise, the kind of movements an animal makes when it has spent its short life staying out of the sight of larger things. If you had been able to see it in the fading light, you would have found it entirely ordinary. A reptile, small, forgettable. Its name, given to it by paleontologists who dug up its bones 150 million years later, is Eoraptor, and it is one of the first animals in the fossil record that can be called a dinosaur. The late Triassic world it lived in would have looked to a modern observer as much like the world we know as like the world the Permian ended. There were forests again, though not the same forests. The giant Gigantopterous trees that had dominated the tropics were gone forever. That lineage had not survived the silence, and the Mesozoic tropical canopy was being rebuilt from different plants, conifers and seed ferns and early cycads, slowly assembling themselves into something that looked, from a distance, like a proper rainforest. The coral reefs had come back in the shallow seas, but the corals that built them were not the rugose and tabulate corals of the Permian. Those had gone too. The new reefs were being constructed by a previously minor group called the Scleractinians, the ancestors of all modern stony corals, which had been almost invisible in Permian ecosystems and was now, in the absence of the old reef builders, taking over the job. And the animals were unfamiliar. The slow-moving, heavily built herbivores of the Permian were gone. The saber-toothed gorgonopsid predators were gone. In their place, a new group of reptiles had begun to diversify across the Triassic continents, the archosaurs, a lineage that had survived the extinction as a minor presence in the Lystrosaurus-dominated early Triassic, and then, when conditions eventually improved, discovered that every terrestrial niche on the planet was empty. They filled those niches with a speed and creativity that the fossil record makes almost visible. Some became crocodile-like ambush predators along the rivers. Some became long-necked browsers. Some became bipedal hunters on open ground. Eoraptor, the small two-legged animal watching the riverbank in the Argentine dusk, was one of the bipedal hunters, a member of a subgroup that would, over the next 20 million years, become the dominant large land animals on Earth and hold that position for 150 million years. The dinosaurs. Not yet impressive, not yet huge, but beginning. What is striking about Eoraptor and the other early dinosaurs is how little about them would have predicted their future. They were small, they were not particularly numerous. The dominant vertebrates of the early-late Triassic were still the crocodile-line archosaurs, the heavy, herbivorous dicynodont descendants, and a variety of other groups that held most of the ecological real estate. The dinosaurs were, at that point, a minor experimental lineage with no obvious advantages over their competitors. They happened to be upright, efficient runners with reasonably sophisticated lungs. These turned out to matter eventually. At the time, they were just one more variation on the archosaur theme, noticed by nobody. Somewhere nearby, in the same late Triassic forests, another lineage was undergoing its own quiet experiments. The cynodonts, the small burrowing relatives of Lystrosaurus that had come through the early Triassic, largely unnoticed, were diversifying too, though much less dramatically than the archosaurs. They remained small. They remained inconspicuous. But across millions of years, the bodies of these animals were being refined in ways that would turn out to be consequential. Some of them developed body hair. Some developed more efficient chewing, with more specialized teeth. Some began to produce live young instead of eggs, though this innovation would take tens of millions of years more to complete. A few of them, late in the Triassic, crossed some evolutionary threshold that paleontologists now recognize as the boundary between advanced cynodonts and the first true mammals, animals no larger than a shrew, nocturnal, warm-blooded, fur-covered, hiding from the dinosaurs that were by then becoming very large indeed. For the next 150 million years, these animals would stay small. They would make their living in the shadows of the dinosaur world, eating insects, sheltering in burrows, surviving on the margins of ecosystems dominated by reptiles that would have crushed them underfoot without noticing. They would not become dominant until the dinosaurs, in turn, were destroyed by the asteroid that ended the Cretaceous. Only then, with another ecological reset behind them, would the mammals finally inherit the planet that Lystrosaurus had inherited so long before. And only then, after another 60 million years of quiet diversification, would one lineage of primates, descended from small insect eaters that lived in the canopies of Cenozoic forests, begin the chain of changes that eventually produced the animal listening to this voice. The entire distance between Lystrosaurus and a modern human is 252 million years of uninterrupted descent, every generation of which had to survive to reproduce, or the chain would have broken. Think about that number for a moment. 252 million years, every summer, every winter, every drought, every flood, every predator that did not catch your ancestor, every disease that did not take them before they had children, every geological event that did not happen to the particular valley where your particular lineage was living at the particular moment. The chain held. Through the Triassic heat, through the long Jurassic reign of the dinosaurs, through the asteroid that ended them, through ice ages and land bridges and sea level changes, and all of the smaller extinctions the planet has staged along the way, the chain held. You are here because of a series of accidents more improbable than the entire history of human civilization put together, and the chain started, in a specific sense, with the animals that walked out of the Karoo Basin in the earliest Triassic. If you had been standing in that basin at the right moment in the late Triassic, perhaps 70 million years after the Great Dying, a short time in geological terms, you would have seen something very different from the knee-high scrub of the immediate post-extinction world. The vegetation was taller. There were trees, not yet giants, but tall enough to cast shade. The ground was covered in an understory of ferns. A river ran through it, and along the riverbank, small animals moved in the twilight. Some of them were early dinosaurs, the ancestors of Tyrannosaurus and sauropods and birds. Some of them were small furred things, the cousins of the animals that would one day become you. They did not know what they were. They were not building toward anything. They were simply alive, in a world that was finally allowing them to be, after the long silence the planet had held itself in for so many millions of years. That might be the quietest way to describe what came out of the Great Dying. Not a triumph, not a restoration, just the patient resumption of biology on a planet that had never really stopped, and a new cast of characters, utterly unaware of their own importance, beginning the work that the old cast had done before them and would not do again. This is how every recovery has worked. It is how the recovery from the asteroid worked 66 million years ago. It is how the recovery from the Triassic-Jurassic extinction worked 50 million years after that. The pattern repeats, with variations. The cast always changes, the work continues. And that pattern, more than any single species or any single event, is what the Earth is. For the last 2.5 hours, we have walked together through the worst catastrophe in the history of complex life on Earth. We have watched magma rise beneath Siberia, force its way sideways into beds of coal and salt, and cook a planet's worth of poison out of the ground. We have watched the atmosphere thicken. We have watched a Mega El Niño that would not end. We have watched tropical forests die and refuse to return. and carbon sinks collapse, and oceans warm past the threshold at which fish can breathe. We have watched the deep sea turn sulphurous, and the ozone layer thin, and the tropical land surface reach temperatures that no vertebrate could survive. We have counted the dead, 96% of species in the sea, 70% on land. We have sat with the long silence that followed, the 5 million years of super greenhouse during which the planet held itself in a broken configuration, and we have watched, across tens of millions of years, life come back. The mechanism of the Great Dying is not simple. It is a cascade of interlocking processes, each one amplifying the next, each one impossible to understand without the ones before it. This is the shape of how the planet fails, when it fails, not through any single blow, through a sequence of blows connected to each other by feedbacks, proceeding from a trigger through an atmosphere, through oceans, through ecosystems, until the capacity of the living world to absorb the damage is exceeded, and what had been a biosphere becomes a record. And yet, what is preserved in that record is not only the failure, it is also the survival. The Lystrosaurus browsing across the empty Karoo in the earliest Triassic. The mollusks walking out of an acidified ocean with their oxygen-carrying chemistry intact, the small cynodonts burrowing alongside them, their bodies already being refined across generations toward warmth and fur and live young. The fungi consuming the dead forests, the mosses and lycopsids colonizing the barren ground. The first early dinosaurs emerging 70 million years later in the forests of Argentina, the first early mammals emerging quietly in the shadow of those dinosaurs, the first early primates 60 million years after the dinosaurs themselves were gone, beginning the lineage that would eventually produce the animal listening to this voice. The chain that connects you to Lystrosaurus is 252 million years long, and every link in that chain is a life that survived to reproduce under conditions that would have killed most of its contemporaries. You exist because the thread did not break. The thread ran through the Great Dying, through the long silence, through the rise and fall of the dinosaurs, through the asteroid and the cold and the ice ages and all of the smaller catastrophes the planet has staged across 250 million years, and it arrived still intact in the room where you are now. Every ancestor you have is a survivor of something. You are the continuation of a line of survivors so long that human language does not really have words for it. This is the first thing the Great Dying teaches. Not that extinction is terrible, though it is, but that survival across deep time is so improbable that the fact of being alive at all is already, quietly, the most unlikely thing about you. The second thing it teaches has to do with the planet itself. Across the 500 million years that complex life has existed on Earth, the biosphere has been through 5 of these events. 5 moments when most of what was alive stopped being alive, and what remained had to rebuild from fragments. The Ordovician event, 445 million years ago, killed most of the marine life in existence. The late Devonian event, 375 million years ago, did it again. The Permian-Triassic event, 252 million years ago, did it more thoroughly than any other event in the record. The Triassic-Jurassic event, 201 million years ago, cleared the way for the dinosaurs. And the Cretaceous-Paleogene event, 66 million years ago, closed the Mesozoic and opened the Cenozoic, the age of mammals, the age that contains human history inside it, the way a sentence contains a single letter. 5 times. The pattern repeats, the cast always changes, the work continues. What the Earth is, looked at across deep enough time, is not any one biosphere. It is the capacity to produce biospheres, one after another, after each extinction, from whatever fragments survive. The Permian forests are gone, the trilobites are gone, the dinosaurs are gone. None of them are coming back. but the Earth that produced them is still producing, still running the slow experiment of evolution across its continents and oceans, still building something, even now, that will be visible only in hindsight, millions of years from some future geologist's perspective. We are inside that experiment. We do not see its shape because we are too close to it. We see only the configuration that happens to exist in our particular moment of geological time. The configuration that exists in our moment is unusually rich. Coral reefs, tropical rainforests, temperate forests, grasslands, polar sea ice, hundreds of thousands of species of beetles alone, mammals on every continent, birds in every sky. It is one of the most diverse biospheres the planet has ever sustained, and it has been sustained continuously for the past 66 million years, since the asteroid, since the slow rebuild that followed. The current biosphere is, from the Earth's point of view, young. It is also, from the Earth's point of view, not special. Every biosphere the Earth has produced looked to its inhabitants like the natural condition of the world. None of them was. There is something clarifying in holding that thought. We did not arrive in a stable world. We arrived in the current window of a system that has always been in motion, and the stability we perceive is the stability of not yet having been through the next transition. The next transition, in whatever form it takes, is coming, not because of anything anyone has done, but because the Earth has never run for more than a few 100 million years without a major reorganization of its biosphere. The only questions that are still open are when, how, and what we have done to accelerate or delay the timing. Those are the questions that paleoclimatology now asks in the present tense. The work of Yadong Sun and Zhen Xu and the others, reconstructing the Permian cascade from rocks in southern China, is not purely a historical exercise. It is a description of what the system is capable of under the kind of stress the modern world is applying. The evidence from the late Permian is that the feedbacks can lock. The evidence is that the carbon sinks can fail. The evidence is that tropical ecosystems, once collapsed, do not recover on any timescale a species like ours can meaningfully plan around. This is not a prediction about the coming century. It is a map of the terrain into which our current trajectory runs. What we do with the map is our decision, not the Earth's. The Earth will continue. The question is which biosphere it will continue with. The Permian biosphere ended and a Triassic one began. The Cretaceous biosphere ended and a Cenozoic one began. The transitions are not always gentle. They are not always fast either. Some have taken millions of years to complete. But they happen, and they happen regardless of whether the species in the biosphere at the time of the transition understand what is happening to them. For most of the biospheres the Earth has produced, no species in them could have understood. The Permian dicynodonts did not know they were in the last days of their world. The dinosaurs did not know the asteroid was coming. The trilobites did not know they had been given 300 million years, and that the 300 million years had ended. We are, in a very specific sense, the first species on Earth that can see the pattern. We have reconstructed the Permian cascade from rocks. We have mapped the asteroid crater that ended the dinosaurs. We have measured the carbon dioxide levels of air trapped in ancient ice. We have built the models that describe the physics of feedback loops in climate systems. We have, across a few centuries of concentrated scientific effort, learned to read the pattern of extinction with precision no previous biosphere could have imagined. And we have learned to read it at exactly the moment when we happen to be acting as a geological agent ourselves. This is the peculiar position the modern human being occupies. We are the only species in the history of life that knows, with any accuracy, what the Earth has been through before. We are the only species that understands, in mechanical detail, how mass extinctions work, and we are also the only species whose activity is currently capable of triggering one. These three facts are not separate. They are the same fact, looked at from three angles: knowledge, mechanism, agency. The three have converged in us at this particular moment in a way that has no precedent. What is done with that convergence is, as we said earlier, not the subject of this series. This has been a story about the mechanism, about how 252 million years ago the sky thinned and the oceans died and the forests fell and the world spent 5 million years in a broken configuration before beginning, slowly, to rebuild. That story is complete in itself. It does not require anything from us. It does not require a lesson or an alarm or a call to action. The rocks do not ask for any of that. The rocks only record what happened. But the rocks are also not neutral, because they are in us now. The information they carry has entered the species that can, for the first time in the planet's history, act on information about the planet's history. Whether that information changes anything is a matter for the species to work out. The information itself is simply available, like a map that has been drawn and handed over and now belongs to whoever chooses to open it. That is, in a certain sense, what this series is. Not an argument, not a warning, a map. The Permian world was beautiful. Not in retrospect, the way we sometimes soften the past. It was beautiful in its own time, filled with gigantopterous forests and coral reefs built by corals that no longer exist, insects the size of small birds, therapsids walking the margins of a single enormous continent under an atmosphere that would not be ours. It was a real world. It had texture and sound and colour. And it ended, completely, over 60,000 years that were, by every measurement we can apply, the worst 60,000 years in the history of life. And yet, what replaced it, eventually, was also beautiful. The Triassic did not become the Permian again, but it became something. The dinosaurs rose, the mammals waited. The planet, through the long unfolding of the Mesozoic and the Cenozoic, produced the world we were born into, with its warm oceans and cold mountains, and the particular colour the sky takes on an autumn evening in the part of the world where you happen to live. The continuity between the Permian biosphere and the modern one is not ecological, it is geological. The same planet, the same atmosphere, the same oceans refilled with new chemistry and new life. The gigantopterous forests became coal beds, and the coal beds became, eventually, the fuel that is now raising the atmospheric carbon dioxide back toward levels those forests last saw. The arc of that loop is, taken in the right spirit, remarkable. The carbon that killed the Permian world is the carbon that might shape the next transition. The same element, the same molecule, moving through the same system, 252 million years apart. The Earth does not notice. The Earth continues. This is its only consistent behavior across the whole of geological time. Continuity through reorganization. The particular biosphere, the particular configuration of warm-blooded animals and photosynthetic plants and oxygenated seas is temporary. The deeper pattern, the pattern that keeps producing biospheres, is not. That is what we learn from the Great Dying once we have walked all the way through it. Not that the end is frightening, though it is. Not that the beginning is hopeful, though it is. But that the pattern is older and slower and more patient than any of the dramas that happen inside it. The planet has been through worse than anything ahead of us. It has come out of worse than anything ahead of us. It will come out of whatever is ahead of us too. The only question is what we come out of it as. And with that question, which we can leave on the table for now, the story of the Great Dying closes. 252 million years is a long way to come. Across all of it, your ancestors survived. Through heat and cold and flood and drought and the rise and fall of every dominant lineage the planet has ever produced, the line held. It held through the Siberian traps. It held through the green oceans. It held through the stripped sky and the lethal tropical heat. It held through the long silence and the slow recovery and the rise of the dinosaurs and the fall of the dinosaurs and the quiet tens of millions of years of mammalian evolution in the shadow of reptilian giants. It held through every glaciation and every interglacial and every major biotic reshuffling the Quaternary has produced. It held through the settlement of Africa and the migration out of it, through the agricultural revolution and the industrial revolution, and every smaller event of human history. And here you are, at the end of that line, listening. This is what the long winter is for, to sit quietly with these immensities, to let the scale of what the Earth has done and what it has endured settle into the shape of a single evening, not as anxiety, not as forecast, as something closer to company. The planet has been through a great deal. It will go through a great deal more. Sitting with the record of what it has survived is a kind of companionship across time with everything else that has been here. Rest now. The planet has done this before. The planet will do it again. There is nothing in the geological record that says the pattern will break, and a great deal that says it will not. The forests that will grow in 10 million years, on continents that will have drifted into new shapes, will not know about us. They will not need to. They will be the next cast in a story that has been running for longer than any mind can properly hold. And they will do their part, and they will be replaced, and what comes after them will also do its part. The Earth is patient. It has always been patient. The quietness you are feeling now, as the sentences slow and the words become fewer, is something close to the quietness of geology itself, which is not silence but the steady continuation of a process that has no hurry. Let that be enough for tonight. The chain held. You are here. The planet is still here. Rest now. The Earth is waiting. Good night.